Humans have always What does the future hold? Excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote progress. A community united by the power of science.
We are all looking for something. Some of us for treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University ICT Museum, the only one kind globally. Visit the main campus and be taken through the telecommunication evolution journey. Information, visit the site at museum.mmu.ac.ke. MMU Museum, with the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does it hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science. ICTP's The Nobel laureate Abdus Salam believed that science is the common language of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Everyone speaks one common language, science. Basic and applied research are both vital for society, from fundamental particles to black holes. Work at ICTP is guided by curiosity and big ideas. This vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here ground for new. These connections encourage brain gain. ICTP's training and education programs support careers. Global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Multimedia as excellence in engineering, ICT, and business studies. Skills and use of iMac computer. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issue. This is our physics chemistry lab, where most practicals happen, including tests on materials, and present research findings to scientists, ensuring safety are met.
This is our computer lab, also known as Korea lab. This is where computer classes take place, and most of the computers are stored with internet.
Morning. I want us to begin our session today on Wednesday. With 2 sessions between now and 10 with 2 speakers which I want to introduce to you. One of the speakers we met sometime think Italy, but he was also Kenyan like me. I remember in that workshop, he won the best poster presentation by then. Dr. Jared, who is a maybe I'm honored also just round of it. This is a friend who, of course, I will easily, it will be easy for me because I've all along his journey. Jared did his Bachelor of Science in Physics at Egerton University. He graduated in 2007. Later on, in the same university, proceeded to do his MSc in Physics and graduated in 2010. Because by that time, the University of Kenya was having a laser lab, but former management. He actually did experimental setup in Multimedia of Kenya in one of our engineering labs. He the potential of this university by then. Later on, he to pursue his PhD research, and he did a especially upper students active at Masai Mara is the patron, which is active, and the first chapter at the same time being an DAD, he has extensively attached a speaker who we need to pay attention to because he has extensive network, which of course into hands together as we were.
Thank you, David, for the introduction. Talking about why shaped technology. So this was university, as David has said. Then this was my PhD in Germany. Currently, I am at Masai Mara University as one of the staff members. Now, we want to understand at the end of my talk, and also we need to get at the end of my talk, understand what is semiconductor lasers. So in the audience, who has heard about terahertz? 1, 2, 3, 4, 5, 6, 7. So terahertz radiation is part of the electromagnetic radiation, and it occupies the region in between millimeter wave or microwave and infrared. And in this region, the study never in high school, in university, to some of us. So it was, or it's called a forbidden. The frequency from 10 power 11 hertz and 10 power 13 hertz. terms of 3 millimeters to around 30 micrometers. That's a lot of potential due to the fact that ionizing quite distinct in the region, and opaque material in this region. So it has a lot of application potential. The biggest challenge is to get the terrace source or terrace detectors. Now, by utilizing electronics and photo technologies, them being filled up by utilizing the optoelectronic terrace generation techniques. So you can have continuous wave lasers. Pulse lasers, for example, can be generated by exciting a pulse laser with a crystal or a photoconductor antenna to generate pulse terrace signal. In most cases, or widely used application of pulse lasers, we call time domain terrace spectroscopy system. And in such a system, the pulse lasers, we use usually femtosecond lasers. In most cases, what we call titanium sapphire. Titanium sapphire is quite a big system. So this has hindered the movement of terrace upset. So to be able to move from the lab setup and bring terrace technology to the market, there is need to develop compact and effective systems which can be brought into inspection in the airports, in the hospitals. So femtosecond lasers are quite expensive, and they are for us to be able to move this technology from the lab setup into the market. There is a need of compact and cost-effective systems. Important source of terrace source is continuous wave. I will talk more on generation of continuous wave signal or terrace wave signal Now, what is semiconductor lasers? Semiconductor lasers is a device that emits light as a result of the combination of charge carriers in the PN junction. Of a semiconductor chip in which you have a cladding and an outer layer which is sandwiched in between the cladding, two claddings. So by inserting or injecting a suitable bias, the active region is able to some light radiation. Now, in my talk, I would like to concentrate on two types of semiconductor structures which I worked on while I was doing my PhD. These are diode lasers. One is I was able to demonstrate stable CW source, demonstrate continuity of CW source. Now, this terrace has a lot of potential in pharmaceutical application because the fingerprint different materials are quite distinct in Terra's range. It is also has a lot of potential in spectroscopy, has a lot of potential in remote sensing. For example, you want to assess the different gases, maybe in a burning can Terra's gun to that building through the pack scattered Terra. You can apply as in quality control, communication, now, why do we want to use semiconductor in our work? It is quite small, they are low cost, and they are efficient. The goal of this work was to develop a compact and a cost-effective system which is stable and tunable for many of these applications. Now, the cheapest approach, which is Terra's photomixing. Terra's photomixing is combining with diode lasers. We are able to develop a compact and cost-effective Terra system, and photomixing is optical heterodyning of two optical signals in a photoconductive antenna. Now, the photoconductive gap, optical bit signal. An optical bit signal, this is a signal which has been developed in frequency. So you excite your photoconductor made of low temperature gallium arsenide, and then field bias the electric fields. The electric fields which are obtained are the Terra's continuous applying source. Now, you have gap with the optical pump, that is the optical bit signal. You generate electron and hole pairs, or what we call photocurrent. These photocarriers, if you apply a suitable bias to the electrodes, you excite them, and in the process, you generate flow of a current. This flow of a current, if you attach a suitable silicon lens, you are able now to connect the electric fields from the antenna. In that process is what we are calling the Terra's radiation. Two signals with slightly different in frequency. Frequencies F1 and F2, and the electric field is E1, E1, and the next signal has an electric field E2, the side omega. If we want to get, or we want to impose, it would be now for antenna it must affect the incident intensity. To determine the intensity, we have to multiply this electric field. So I will be approximately equal to T. the values, that is the half E2 plus the a half E1, their half time is faster than the carrier which is generated in the semiconductor material here. So the higher are ignored. Take the negative value, which is slow value, which can be able to be detected by the system or by the photoconductive antenna. So your intensity will be approximately equal to E1, E2, the cosine of omega 1 minus omega 2. The Fourier transform of this intensity, what you obtain is the terrace radiation. Now, in photomixing, the conventional systems usually employ two lasers which are independent but with slightly different in frequency or in wavelength. So to be able to stabilize these two systems, you will need this system more complex and more unstable. And also, to be able to align these two beams is not easy. Maybe you could use optical fibers. Maybe you could spend of your time in rearranging these two beams so that they are on top of each other. So to solve that, we had to utilize just a single laser diode. So setup, it is easier to align the two modes with one laser chip, and also you have a reduced simplified setup, and in terms of cost, it will be reduced. So where do we require stable optical sources? We require them in medicine. If you want maybe to do some imaging, you need stable source in astronomy, you need a stable source in communication, and in quality control. You require a tunable system for pharmaceutical because different materials have specific signatures, different wavelengths. So in the first case, I utilized a monolithic 2-color DBR laser, which was emitting at 785. So the first beam was around 785, and the second beam was at 785.6 nanometer. If you get the difference in wavelength, you get this is around 0.6 nanometers. From this, we can calculate the optical beat frequency to determine to determine our system, what kind of terrace CW will it produce. So this system was able to produce a terrace radiation in the range of 200 gigahertz. So in first case, I had to determine the stability system and can we be able to get stable terrace radiation. So as you can see, as you start from 0 to around 180 milliamp, you observe some mod jumps or mod hops. But 180 to around 200 milliamp, you get a stable regime. So we could be able to generate stable terrace radiation in this range. And this is around 300 gigahertz. So radiation, for example, but in this case, they employed 2 laser diodes, as you can see here. So instead of using these 2, it is possible we could utilize our system for the application for such a system. Now, how do you generate now the terrace radiation? Now, by sending the, you send it into a beam splitter through the ray stage to the transmitting photoconductive antenna signal to the detector, that is the photoconductive. The transmitting antenna, you get it modulated with a frequency. This frequency is then connected to the lock-in amplifier and the transimpedance amplifier for detection. The current which you detect by translating the ray stage will appear like this. This is what you obtain as the generated photocurrent. By applying Fourier transform, that is time signal into the frequency signal, you obtain the terrace frequency at around 0.3 terahertz, 300 gigahertz. Now, the next work was to now improve on what we are demonstrating a new is. So in this case, we employed this structure, and in each section, this DPR, it is independent to a current. The process change the wavelength which you are. So by combining the two beams at this side, you any disparities, and you get a signal. So this is the developing attainable terrace. So optical beat signal look like. Now, the structure also emits around 785 nanometers, and by varying the ether current in the DPR grating, we was able to tune this structure in this range. However, at higher ether currents, you obtain that these two modes overlap. At this region, you don't expect to obtain any optical beat signal because the difference here will be zero. Two modes, higher currents where the two modes overlap, you get a zero. So terrace generation ability of the system when in the frequencies from 0.18 terahertz to 0.3 terahertz. Now, by applying longer scan of the direction to the spectral resolution of about 4 gigahertz was to check our signal as the generated terrace signal like modes, and this have a spectral around 15 gigahertz structure, which had in the singular modes there were some multi-modes. So we wanted now to investigate whether we could be able to use this for communication. So we employed the terrace setup for spectroscopic application and metrology, and in this case we employed TPX lenses and Teflon lenses for focusing our terrace signal into the sample which we are investigating. So in this case, for spectroscopic employed a bandpass filter operating at 250 kilohertz, and for metrology, I employed the determination of the thickness of a polyethylene sample, which was 3.1 millimeters as measured by the vernier caliber. So for spectroscopy, we inserted our sample in the optical path, and then fine-tune the Terrace frequency using the current electronically. So by determining transmittance versus the frequency at different ether currents, we are able to determine that measurement. This is our measurement, and it corresponds well to the measurements which were the manufacturer, that is Tidex data. Further, we evaluate this sample, and we can see here that the bandpass filter was also in agreement with our measurement. So this is an OSCAT system, a very huge system from Mainlo, Germany. So the next item was to evaluate whether we can use our system for metrology, polyethylene sample. So in this case, we utilized the multi-frequency with and without the sample. What we did, insert the polyethylene sample in the Terrace path, and then map the Terrace frequency with and without the sample. So the measurement, our reference, and measurement with the sample will now be used to evaluate the thickness of the sample. If we subtract these two multimode frequencies, we were able to extract the initial position of the signal and the new position or the shift of the signal due to the insertion of this polyethylene sample. So from this, we apply this equation. The change is equivalent to n, determine our thickness. So in this case, we employed the refractive index for this sample of 1.54. We were able to obtain a thickness of approximately 2.62 millimeters. This is quite close to the measurement which was done using the vernier caliber. However, we thought that the index could have been different in the video we used, hence the difference. So in brief, I have demonstrated, or I've talked about a stable Terrace source based on a monolithic two-color laser, and also tunability based on the electrically tunable monolithic two-color DBL laser. With that, I would like to acknowledge my supervisor, Professor Martin Hoffman, who mentored me, and our research team and my family. Thank you for your attention.
Again, let's give him one more hand clap. Any questions from the speaker, from the floor? Any question? Online platform? No question? No question? Oh, we have a question.
Thank you for the presentation. Maybe I missed it. How stable are these terahertz radiation sources?
It depends on the system which you use. The stability comes from the exciting laser. So if you have a stable system, that is stable lasers, which is you are using to excite the antenna, very stable signal. Yes.
Okay. Thank you.
Thank you. More questions? Any comment? Alessia, you seem
Thank you, Jared, for the presentation. So I just wanted a comment in regards to, you have said one of the challenges of this kind of system is the fact that we are required to use maybe past femtosecond laser, which is a little bit bulky. And in future, you think that maybe it can find more applications if it's portable enough.
Yes, yes.
So are there some potential studies that have shown the portability of this?
Yes. For example, there is a group in Bari which is working on compact semiconductor sources. They are the size of the camera for wireless communication. So there is potential.
Thank you, Jared, for the nice presentation. We know now that there are many applications. You are using mainly this generation. You have to
Yes.
you are converting. In some application, I don't know in terahertz, I am asking. For example, in visible rank, it's important to have to consider the bandwidth of the, and when you convert in different frequencies, it's also important.
Yes.
What about terahertz?
Yeah, the use pulse lasers. It has a wider band free. You can go from 0 up to lasers 5 terahertz. So for CW, because it's a single signal, the by if you get wide, for example, you have like 800 and then you have 810, the two peaks, that band is quite broad. If you saw here, I was working from 785 to 780, 0.6 nanometer wave difference, but we were able to generate from 100 to around 300 gigahertz. So if you have a broader two modes separation, you are going to get a of the different signals. So the bandwidth is the bars lasers
have not closed anybody out. Maybe just most of this a bit astronomical. Maybe actually
20, I think 22, it was working here. Currently, in future, we will have to work together.
Thank you. There's another question.
I saw, for example, to use pulse laser is a little expensive, not to
Yes.
do this research.
Yeah.
But is it possible to do also terahertz low cost?
That's why I was the semiconductor diodes. They are cheap. Yeah.
And maybe an eye opener you to be able to align yourself. We have our own local researcher who is working in this field. Thank you. Let's clap again.
Thank you. Thank you. Let me check.
We are going to the second presenter for today, who is joining us virtually. The next maybe 10 minutes or so. Johnson, you can hear us? Next speaker is Johnson Kalwe, but we are having an issue with connectivity. Maybe we to connect from his end. Before I just give an introduction about Johnson. You can hear us kindly. You can just say hello. We can hear you. Maybe it's the sound on our side.
Recording in progress.
Try to.
This is the point has mass.
Share your screen. I can hear you. Clear. Johnson, are you able to share your screen? We can't see your presentation. You can hear us? Hello? You can hear us? We are to share the screen. Okay. Screen. Just maybe wanted to make a short introduction of his, at the National Institute for Optics, 16 hours away, doing his the Department of Physics, Harbin Institute of Technology. As a short background, Johnson did his BSc in physics at the University of Agriculture and Technology, where he actually earned, not obtained, but earned a first class. Later on, he got a scholarship, which was a sandwich with the Planck Institute, together with the department at JKUAT. He did his MSc with in lasers and optics, and graduated at JKUAT of Kenya, where he has been a staff, and likely he got scholarship to do his PhD in the same field. So I want to give an opportunity to Johnson to give his presentation. Welcome.
Good. Thank you so much, Dr. for the introduction. Okay. The next problem. Let's struggle. Struggle.
Johnson, we can hear you.
Hello, Dr. Are you able to see my screen really?
Yes, we are seeing you.
Good. So thank you so much, Dr. for that introduction. And sorry too for the technicalities that we are facing trying to connect. There is a problem with the VPN that we normally use to be able to use some of the Google services like the Zoom. That's why we are facing the kind of challenge that we are. Are you able to hear me before I proceed?
Yes, we can hear you.
About metaservices integrated dialectically chirometalensis. Professor is Professor Ching Lee of the School of Physics at HIT. So this is how I intend to give the presentation. I would start by giving an overview of chiro-light matter interactions. Then we look at variation in chiromedia, measurement of chirophysical effects. I will introduce us to some previous research activities, then take us to the current research works in relation to chirooptics. We'll also look at the dialectically chirometalensis. So we start with the chiro-light matter interactions. And by definition, we say that this refers to the dissymmetrical interaction between light and matter, which results from the non-symmetrical arrangement of atoms in chiral materials. And by definition, we refer to chiral materials as objects, so that when we have an object and its mirror image, there is no mirror symmetry, and therefore this object and its image cannot be superimposed. And as a result, when light is going through this chiral medium, then it experiences different optical responses that results into what we define as the chiral optical effects. For example, as we can see, so as you can see in this diagram, if we have linearly polarized light going through a chiral medium, then we experience rotation of the polarization of the linearly polarized light. And for this phenomenon, we refer to it as optical activity or simply optical rotation. Now, if we have circularly polarized light going through the chiral medium, there are two effects that happen depending on the nature of the medium, whether it is 3D or 2D. For the first case, if the material is 3D, then we experience differential absorption or differential transmission of either from the hardness of the CPL, circularly polarized light, and that results into an effect, an optical response that we refer to as the circular dichroism. Now, for the case of metasurfaces, when we have circularly polarized light incident on the chiral metasurface, then it undergoes polarization conversion. So that if we had sent in left, then the result is right. If it was right, then it's converted to left. And such optical response, we refer to it as circular conversion dichroism. And this I would speak more about the circular conversion dichroism more because I am working on metaservices. Now, chiral materials are categorized into two. We have the 3D and 2D, both of which can be classified as either intrinsic or extrinsic. For the case of intrinsic, as for the case of 3D, then we say they have some sense of twist. For example, if you look at this figure here of an hélice, if one looks at from the top, from the bottom, then the sense of twist is different. This, in the case of metaservices, we talk of mirror of symmetry. And for such, we say such a 3D or 2D metamaterial is chiral. Now, that chiral, the symmetry can be also broken through the interaction of the medium and the wave, what we call when we have the incident light at an angle, and we say the chiral is we can also achieve chirality by combining a number of geometries. For example, what you are seeing here, we have a chiral structure that are combined together to constitute a unit cell. So the net effect is that when we have the light going through, then there would be different responses for either of the light-handedness. Now, this chirality is also exhibited in natural materials. For example, in this figure here, I show some of the natural occurrences for chirality. For example, in the single wall carbon nanotube, as shown here. Also, here we have an example of a tunneling microscope, and we have this object that is familiar to most of us. That is the seashell. We also have a DNA double helix, which also exhibits chirality. Now, for 2D meta materials, which we have defined as the meta services, we have an example of 643 nanometer gold monocrystal. Now, to bring the chiral effect, the chiral optical effects to perspective, then I show schematically the difference for when we talk of the 3D chiral media and the 2D chiral media. For example, now if we have right circularly polarized light through a 3D chiral media, then we can only get a differential either absorption or transmission without polarization, without conversion. And if we change the direction of propagation, for example, you can see this is from left to right, and this is from from right to left, then there is a difference or there is asymmetry in transmission, which for left and right, which results into the CD, the chiral dichroism. Now, For the case of a metasurface, there is conversion. We send in RCP, LCP, sorry, we get left. And there is asymmetry when we change the direction of wave propagation. For example, in this case, we see the left circularly polarized light is less in comparison to the forward propagating. And this is a phenomenon that we are going to look at and address ourselves to it more. Now, these phenomena that we have just here, we can give the physics behind. So, of course, we have the Maxwell's equations, and for us to be able to describe how to discuss the wave propagation in chiromedia, then we are guided by some constitutive relations which relate the fields. And for this case, we are going to make use of the Telegen's constitutive relations, which relates the field, the electric and magnetic fields, through this parameter here that we are going to define as kappa, the chirality parameter, or the the chirality parameter, which couples the electric and the magnetic fields. Now you realize from these expressions, if the chirality parameter, the kappa, is 0, then the expression reduces to the basic Maxwell's equation that we know about. Now, from this equation, we can also see that when we have a plane wave incident on the chiral media, then it has different wave propagations for left and right, as shown by equation 2 here. And similarly, we can represent the same in terms of the refractive index. For this case, the plus and minus, we are using them to denote for right and left circularly polarized light. So the refractive index for the right circular polarization would be given by the effective refractive index plus the kappa, the chirality parameter, while the refractive index for the left circularly polarized light given by the effective refractive index minus kappa. So as a consequence, then we are able to get the first chiroptical effect. That is the one for circular birefringence resulting from the different refractive indices. And we see for the refractive index of the left circularly polarized light, when the chirality parameter is more than the effective refractive index, then it also results into a negative refractive index, which is a very important phenomenon in optics. Now, this optical, for the quantification of the chirality effect, then we use the optical chirality density that is defined in terms of this expression, which basically relates the pseudo-scalar product between the electric and the magnetic field. And from this expression, you can say that when the electric and the magnetic fields are parallel to each other, then we have concentration or confinement of the electromagnetic wave through the structure. And if these fields are perpendicular to each other, then it results into destructive interference, and there is minimal confinement of the wave into the structure. And next, I look at the measurement of the chiral polarization effects. So on this side, we have the source. We have the source of the EM wave going through the chiral media again to the space. So through the chiral media, it can either be transmitted and reflected, the scattering happens. So part of which is transmitted, and there could also be some reflections depending on the nature of the chiral media. And for the quantification of this chiral effect, then we normally use the complex Jones transmission matrix, which normally relates the incident electric field and the transmitted field through the transmission coefficient. And for this case, of course, the polarization of the EM wave is very key. For example, in this expression here, we can see that we have I and J, and this is to mean the polarization of the transmitted light in response to a J polarization. Now that we are talking of circular polarization, then we need to rewrite the Jones matrix in terms of circular basis, and for that we introduce the components, the co-polarization and the co-polarization and the other cross diagonal components, which give us the cross polarization. Maybe just a brief on how we read these components is that I had said earlier, the plus denotes right and the minus denotes left. So in this case, then it would mean the incident light is right, then the transmitted is right. Here the incident is left, then the transmitted is right. There's conversion. Now, for 2D chiral materials, then the chiral responses, that is the asymmetric transmission and the circular conversion dichroism, are calculated as one, the difference between the transmittances between the cross polarization components, and this is how we calculate. So from measurements, we obtain the coefficient, the transmission coefficient, and we can calculate the transmittances through this expression. So the first chiroptical effect, which is asymmetric transmission, is given by the difference in the cross polarization components. And the CCD, the circular conversion dichroism, is given by the ratio. If we were talking of 3D metamaterials, then would be interested in the co-polarization components only. Therefore, these expressions we have here would be using the diagonal components of this matrix and not the leading components. Now, some of the work that have been done in relation to understanding and studying the chiral-optical effects, and more so towards enhancing the chiral-optical effects, I want to present some of them. One is a case where the metasurface comprises of an array of chiral graphene metasurfaces, and for this they were able to obtain the transmission spectra for the cross and the polarization component when the metasurface is eliminated from the forward direction and the backward direction. And from the results, they are able to show that once that happens, once we illuminate this metasurface from either sides, then there is an asymmetry in transmission. As we can see from this spectra, is that the transmission the conversion from left to right in the forward is inverted when we change the direction of propagation, and that is an aspect that I mentioned in the introduction. Some other works in the same area was done by Chang et al. In 2021, where they reported a collection of meta atoms that constitutes their supercell. And with this structure, the material for the structures was germanium and mounted on a calcium fluoride substrate. So for this, they were able to enhance the circular dichroism by some good extent. And on top of enhancing the circular dichroism, they were also able to demonstrate that their metasurface has a polarization dependent focusing effect. And this, I'll be able to demonstrate this effect later in my work. Some other schemes that have also been adopted similar to this work, okay, where the supercell also comprises of meta atoms that have been designed to enhance the CD, the circular conversion dichroism effect. And also they are able to demonstrate through these intensity distributions that is also able to achieve polarization selectivity. Now, with this background, then we look at the problem statement that is motivating us the work that I'll be discussing in a few. And we see one that in these metaservices that are shown here, they comprise of a number of unit elements. And this makes the structure to be bulky. And our end objective is towards achieving miniaturization of devices. So this arrangement complicates their optimization because we have a number of meta-atoms in the unit cell. So this complicates the optimization and also fabrication. And we have seen in other cases where they use cascaded geometries, which also limits compactness and fabrication ease. So these are some of the geometries that I just mentioned. And as you can see, I've said that they complicate the optimization. This is an example where the geometry are cascaded. Now, the justification to our work is that we want to propose, want to use a dialectically chiral meta-atom in comparison to structural chiral atoms that have been, structural chiral, structural chiral meta-surfaces that have been previously discussed. So in our work, we intend to introduce the electric chirality parameter in the structure. And for this, then, it is going to break the chiral asymmetry so that we will get different responses for the different handedness of circularly polarized light. So now I take us to the current research activities that we are looking at. So this is the schematic diagram for the metasurface that we have designed. And for our work, we are simulating using control multiphysics. So from this structure here, we extract the unit cell that from the software that we're using, then we use the periodic boundary conditions along the x and y, along the x and y axis, so that we can simulate infinite cells, so unit cells to constitute the metasurface. And along the y-axis, we have the periodic boundary conditions, and we also include the ports, the input and the output ports along the y-axis. Now, the material for a nanofin we choose to be titanium oxide, and it's mounted on a glass substrate. The dimensions of our meta atom are as shown, and we want to design our meta surface to be able to operate in the feasible wavelength, though specifically our design wavelength is at 532, but we are going to demonstrate that it has a broadband transmission characteristic. Now, the motivation, so the first thing that we do is to measure the transmittance spectra at our dielectric polarity parameter that we have introduced into the structure when it is at 0. And then we vary the value of K and also observe, try to observe the response. Now, so from this graph here, we see all we obtain the the spectra at kappa is equal to 0. And we can observe that the spectra for the core polarization and cross polarization component is identical. But we can also note that the cross polarization, for example, the red and black here, the black denotes when the incident light is right circularly polarized and the output, the transmitted is left. And for the right is left incident and transmitted is right. So we see that they have characteristic high values for the for a broad wavelength range. And the first thing that we note is that the polarization conversion has happened, whereas the co-polarization components are seen to be at minimal values. Now, when we change we change the chirality parameter to some value like 0.04, we take the imaginary value, in this case, the imaginary value of kappa, because we are interested in the differential transmission. So we note that there is a separation in the transmission spectra, and this tells us that that the kappa that we have introduced in our structure plays a role in the chirality, in the differential response of the right and left circularly polarized light. As we can see from this spectra here, if we can follow the spectra for left to right transmittance, then we see at a wavelength of around 440 nanometers, there is a characteristic dip, which is not seen in the spectra for when K is equal to 0. And as we grow in the spectra, then we also observe another characteristic, a characteristic peak at a wavelength of around 460. Now, this spectral splitting of the spectrum implies, so is a consequence of the dielectric clarity parameter that we are adding to the structure. Now, we note that on increasing the magnitude of the chirality parameter, so is the separation, the spectral split widens. Now, it's also worth noting that unlike in other observations that I'd shown earlier, is that also the dielectric parameter, sorry, the chirality parameter that we are introducing in this structure also influences on the core polarization components, as we can see also evidence in the split, implying that the chiroptical effect that we are going to see in the coming slides is as a result of both the cross and the copolarization components. Now, the next thing that we do is also to see the effect of the chiral response to when the kappa is plus or minus. So we set our kappa to be have a plus value and a minus value. And we see from this graph that there is a spectral inversion. And this compares well with the Paradis effect. Now, from these measurements, as I said earlier, then we calculate the chiral-optical effects, and key of the effects that we want to look at is the circular conversion dichroism, and I've used here T to imply that our meta surface, we are focusing on the transmission. And this is the formula that we use to calculate for the circular conversion dichroism. And this is the spectra that we obtain as a result. And we can see from these results that as we increase the value of kappa, so is the CCD. And we can therefore say that unlike with other schemes where they are making use of complicated geometries, we can be able to use a simple geometry and attain a tunable chiral response. Now, additionally, we also measured or we calculated for the chiral density from this formula that I had shown before, and from this near field intensity, near field near field distributions, we can see, for example, in the case of k is equals to 0, for the first case where we have right circular polarization, then we see that the fields are strongly confined in the structure. This is our structure that is represented by the dotted lines. So for the first case, we have right circularly polarized light, and the figure 2 here is for the case when we have left circular polarization indent onto the meta surface. Now, as we increase kappa here, then we note this behavior is the same, but the intensity increases. All the confinement is more. Now, with this result, then we can our structure can be applied, especially in integrated functions, and it can also be used in chiral sensing and imaging, also that we are able to sense the handedness of the circularly polarized light. Now, with these results, then we make from this result. Then it was possible for us to design a dialectically chiral meta lens as an application of the dialectically chiral meta surface. So before I look at the work that we have done, then I want to give some background into the design of the meta lenses. And the first thing when you are designing the meta lenses is to define the target phase profile. And from after defining the target phase profile, for example, in our case, in the case of a meta lens, then we are interested in the focusing profile, and we'll be keen on the spherical lens profile. So after identifying the phase profile that we desire, then the next thing is to identify the modulation scheme that we can use to achieve this phase profile. And there are 3 modulation schemes that we can use. We can use the resonance base, and we use the resonance base when we are working with the metallic elements. But for our case, we are working with the electric material. And so we narrowed down to two of those modulation schemes. That is the propagation phase modulation here, where the phase modulation is acquired by varying the height or the diameter of the metal atom. And the other modulation scheme is a geometric modulation scheme where the phase is imparted or is acquired by rotating the metal atom by an angle theta. And for this design, then the metal atom is designed to behave like a half-wave plate. And the full phase coverage is achieved when the metal atom is rotated by an angle of between 0 and 180 degrees, so that we can get a full phase coverage of 0 to 2 pi. So the next thing, after identifying the modulation scheme that one is to use, then we do the phase to radius or the phase to angle matching, so that we can come up with the overall design of the metal lens. This I'll demonstrate in the coming slides. So some of the work that have been done in relation to chiral metal lens involve structural chirality. Again, as I mentioned earlier, the structural chirality impairs optimization. Now, even though researchers have been able to get good results with the chiral meta services, they still are bulky, and they also so another related research is on optimization of these meta lenses. Yes, we have the meta lenses. Then how can we optimize them? And from this, the paper they're using propagation modulation. It's not possible it's not possible from these works to attain the polarization conversion that we desire. But from this paper, it's possible they are able to demonstrate that with the dielectric metal lens, we can tune the focusing properties of the metal lenses. So in our work, we want to combine the chirality effect, where we can be able to show the differential responses for the right and left, and also demonstrate that we can attain a tunable focusing effect in one. So this is the design scheme for our metal lenses. The red and the blue represent right circularly and left circularly polarized light. And each of these metal atoms are arranged on a glass substrate, so that at every position, each nanofin or each metal atom is at a specific angle. Now, the first thing that we see is that as we rotate the unit cell by an angle, then we are able to attain rotation from 0 to 180 degrees, we are able to acquire a full phase of 0 to 2 pi. And the phase, there's a linear phase relationship as we increase or as we rotate the metal atom in this angle range. Now, we also note that as we change the chirality parameters we had shown in the earlier example, is that we are able to increase this transmission by 4%, which is important, especially when we are designing for optical devices to be used for practical applications. So from these results, then we are able to make use of these formulations for the phase profile and the formulation for anchor of rotation of each of the meta atom, so that through actually we make use of these expressions when we are writing a code in computation for us to be able to map the phase to so that we can be able to get this arrangement of the meta atoms. Now, so for our designed metal lens, we add to trade with the numerical aperture, so that, of course, from the values that we have here, we designed a metal lens with a numerical aperture of about 0.54, which is good enough, at a wavelength of 532 nanometers. So from this metal lens that we designed, one, we illuminate the lens with the either simultaneously, all with either left and right, and we can see from the profile that I'm showing here is that for the right circular polarization incident on these metal lenses, then we have strongly focused at a distance that is equivalent to the focal length. And when we switch the handedness from right to left, then we note that there is a defocusing. There is no when the incident light is left, then there is no focusing. And this is good because it tells us that our metal lens has the polarization sensitivity. You can sense between the left and right circular polarization. Now, we go ahead to characterize the nature of the wavefronts or the nature of the focusing. And we see, as shown in this figure C and D, for the case of right circularly polarized light incident, then actually we see the wavefront is spherical, and this conforms to the convex nature of a lens. So it tells us that with this metal lens, it can function as a convex lens, and at the same time, depending on the polarization of the incident beam, it can serve as a diverging lens, as we can see from the wavefronts of from this wavefronts of this figure here. So from these results, then we do characterization of the focusing performance of the focusing, and we measure the focal intensity at the focal spot here, and measured the full width at half maximum. And for our case, we obtained that value, the full width at half maximum, at 0.51 nanometers, which is less than the design wavelength, implying that still our metal lens is able to focus light to diffract to some diffracted limited spot. And the focal depth again of our metal lens is comparable to is at 6.0, which is still comparable to the our focal length, which is at 5.5 micrometers. Now, our interest in this research is to understand or to see the effects of the chirality parameter on the metal lens. So, in the next stage, we vary the chirality parameter in our structure, and we see from these profiles that as we vary the chirality parameter from 0 to about 0.8, then we see that the focusing intensity is seen to increase, and that is That is the key point in our. I mean, this is remarkable in our research because we are able to demonstrate, as shown in this figure here, that as we vary, or we can be able to tune the focusing intensity of the meta lenses by simply varying the chirality parameter of our structure. And this is important because it expands the range of applications for meta lens, such as in adaptive optics or dynamic imaging systems that require rapid focusing intensity and adjustments. So for this, I would want yeah, so this brings me to the end of my presentation. These are the references that have some of the references that I've made use of. And for the remaining minutes, I want to invite my colleague, my senior colleague, to speak something about part of his work. Hello?
Yes, just go ahead. We are waiting for. Presentation. Your colleague can go ahead. Introduce him.
Yes, I can, but the sound is great.
From the floor as we wait. Like we have a question on the platform of the 2D material polarization effect. A question from you can respond.
I think, Daktari, are you able to hear me?
Yes, we Johnson. We can hear you.
Got the question, and indeed, yeah, the substrate has an effect on the transmittance spectra, and that's why when from the results that I did show here, we can see that the co-polarization components are still present in the metasurface. Remember that for the case of metasurfaces, then from these expressions here is that the co-polarization components, which are associated with the 3D metamaterial, are not supposed to be present, but the thought that we component which is associated with the substrate.
Thank you. Clear enough. More questions from maybe the floor? More questions for Johnston? Johnson?
You can hear me.
Clear? Clear? Got it.
Good.
Is your colleague on near you? Johnson, is your colleague in the lab near you so that we can hear him? So in the meantime, Johnson, you are with me? You can hear us?
Yes, I can still hear you.
Thank you. I think we can thank you for your presentation, and we are going to have you maybe in the next sessions. Your colleague can join us online. We can connect him. So in the meantime, let's clap, put a hand clap for Johnson. Thank you so much, Johnson. I think we can have for tea, so that we come back for our next presentation. Maybe how many minutes? Yes, maybe for about 20 minutes is enough. Thank you. We'll be back at 10. Maybe. Thank you.
No. Anyone who is unable to see this window, you press S and drag like this, and once you release your, you should see this window. With us, right? Anyone left behind? Okay, good. Next. Everybody is able to set the as 30. Yes. Anyone? Oh, there is one person at the back side. Just please help.
Nataka Swahili wageni wasisikie. Tafadhali wanataka certificate, they must attend the sessions. And they must sign the attendance. Otherwise, give certificate for the friends who have left, they come back. Otherwise, they will not get the certificate.
You know what you have to do. Press S, then whatever you want to sketch, you have to do it from here. Okay? Yes. Okay, great. Okay, let me tell you, those who are confident can go fast. You have manual on your desktops. You can try to go a bit faster. But those who are a bit slow, they will follow us. But I will request, it's better that all of you just follow us, okay? Okay, next please.
So now we need to add 1, 2 and 3 lines in the way they are they can be seen in the picture. So you have to again press at the line, right?
Again, press line. Yes.
Yes. Press S and select the line tool. Then you take your cursor to the boundary of outer circle, and it will show you the tangential points. So if you can see the tangential points at this point.
Everyone can see these yellow tangential points on this orange border, right? Very good. Yes.
Yes. Yeah. So now you have to go to the upper tangential point and click the mouse button and drag it outwards, right? Drag a little bit, and now you have to follow this guide, right? This yellow color guide. You have to follow it and take it to there. Okay. Now click again, click, and you see that line still continue. So it shows you the vertical guide, and you have to follow the vertical guide until you see another guide to the lower tangential point of the circle.
Everybody is until here. Press S, draw a line, and then drag it to the down so that you can see this guide. All of us can do, right? Very good.
Okay, so once you do this, the line command is still active, and you have to press escape to get rid of it.
Now all of us can do this, right? Yes. Anyone who is unable to reach to this level? Anyone left behind? Whenever you have to give dimensions, press S, use.
Your attention to this line. If you see,
look here, please look over here. Broken line.
Disconnect.
Okay, you can.
Okay, so should we continue?
Everyone, should we continue? Yes. Okay.
Okay, so entities as construction geometry, and now
at the last row. Okay, please stop. Please
yes.
Press S, then select trim entities. Go to the left. Option. Last row. Are you with me? Okay. Now go back to your original sketch. Do the same thing as you have done before.
So you have to trim this line again, and you see now the trimmed line is shown as construction geometry.
Okay. Of your cursor, move your mouse from here to here, then this boundary will be like trimmed. Still will be the part of your sketch. Last row, are you with me? Okay.
Okay, so now trim it again, and you should see a construction line like this.
Now
so if someone has completely deleted the sketch, it is also fine, but this was just for
okay,
that we can keep the entities as construction, right?
Okay, wait. Everyone has a sketch like this? Everyone? Please raise your... Everyone, are you with me? Do you have this sketch? Now we are going to the next command, okay?
Right. So, okay. Sketch. So as control, see this kind of interface. So a sketch is the boundary for your part. So we have successfully created the boundary.
Sketch to see that is okay as per our requirement. Move your sketch. Are you able to move the sketch? No. Press the Bilal, please open the SolidWorks window.
Yes.
Click the
center button and move.
You have
You have to press the wheel and rotate.
Yeah. Now I have to extrude this sketch. Like this is the boundary, and now you have to bring or add material to this sketch.
Wait.
For that, you have to use extrude.
Wait. Everyone, now go to the next step of the. Please look at this. Now we are going to do this step. Okay, Bilal, please.
Just
Okay.
now
So-
you see, if we want to extrude, what should we do? Press S, right? And then
So
S.
once you press S, you see that extrude boss base command is not there. So you have to extrude. Okay, and you extrude boss base. Can you search and see
Now
this?
keep it here.
This extrude in the search window, EX, right? And then you can this extrude for backslash option, right? Click this.
You see this? If you hover over the extrude boss base command, you see a plus icon.
Click on this.
So let me do it again for you. Press S. Extrude.
Okay.
And you can see this command here.
Of your mouse and hold and then move.
And then you press the add command, insert command option. As should appear here.
Okay. Everyone has added this.
After every entry dimension, you will click OK or simply press enter, and the command will finish.
Wait.
Now you should see this kind of structure in your canvas.
Everyone, have you this?
Yes.
Every row. Okay, great. Now Bilal, move to the command.
Now the sketch can only be started on a plane or on a surface. Okay. So if you write any plane, you get an option to start a sketch, or you click any surface, get an option to sketch. Okay. So
you
now
can.
in your manual.
Okay, everyone. You can sketch on a plane on a surface. Okay. So please SolidWorks
Right.
screen. Bilal,
So yes.
please show the SolidWorks screen. Okay. So you can only sketch on a plane or on a surface. Okay. Now what we are going to select top surface and draw a circle on that surface. Okay. Please go and top surface sketch.
Okay, so for that, you have to right click the top on the top surface, go to top surface, right click. You should be able to see this kind of window.
Keep it in. To the top surface, select and this window will appear. Right click and this window will appear. Everyone, are you with me? Yes. Okay. Now select the second option in second row. Sketch.
Okay. So sometimes you accidentally select edit sketch, but you have to avoid it. You should select sketch, click it. Once you click, SolidWorks will automatically right? So you are seeing this surface from the top.
Everyone has selected the sketch on the top surface. Everyone is with me? Yes. Okay. Now press
So
S.
yes.
Now
So you
press.
should see your model like this. For a Right? If you have a vision, then your sketch is started.
Okay.
Now,
Everyone has a sketch like this?
Yes.
Okay. Now please press S. Press S. And select the circle. Press S. Select the circle. Go to the origin and draw the circle.
Yeah. And you be greater. Okay. So, have you drawn the circle or at this surface?
On the top surface, you have to draw another circle with the diameter of 20.5. Okay? See this one. Or on the plane, it looks.
Circle?
Everyone has drawn the circle?
Yes.
Okay.
Yes. So if you have a circle, now I would like to ask you that how I can get into this circle.
Now everyone, have you drawn the circle? Yes. Now try to give dimension to this circle according to the manual.
So the method was to press S and then click the boundary of the circle.
Okay, wait. Everyone, please press S. Select the smart dimensions. After giving dimensions, enter. Now your sketch should look like this. Everyone is with me?
Yes.
Okay.
Okay. So if that is the case, then move your model a bit, and you should see that the sketch is made on the top surface.
Please stop.
Yes.
Now, please move your structure. So, how you can move your structure? How you can move your structure?
Yes.
Press the scroll button and move. Your structure will rotate or move according to the movement of your cursor.
Can you do it?
Something that you want to control the dimension of your beam. The reason is that, I don't know if you remember, but I mentioned the fact that it is important to control the thickness of the light sheet, because if you have a light sheet that is thick, then you will excite the fluorescence from a thick layer. So you don't have a good axial resolution. If I can, but if the light sheet is thick, the long relay length, which means that your light sheet will be homogeneous in space. So it depends. Sometimes you want a very thin light sheet and a very short relay length, because maybe your sample is small. Other times you prefer to have a longer, let's say, light sheet and a thicker one. What can we do? Well, with either a very large beam, and indeed that will give us more focusing effect, or we can have a sheet and then the focusing of this beam, and then the focusing, the capability of a lens for focusing it will be reduced. So we will have a thicker light sheet and a longer one. So I want to expand the beam. That's what I want to do. So that I have, then I can play with it and I can make it smaller or leave it untouched, depending on what I want to do. How do I do that? Here I have the first lens. That is, this is a 53 millimeters lens, 53 millimeter focal length lens. So what does it do? It focuses the beam in one dot, in one very small dot. This is the focal plane, more or less it's here. You see that it's focusing. So this is what a lens does. Focus. Okay? It becomes larger and larger and larger, and it is larger. If I place the second lens at a distance from the focus of the first lens that is equal to its focal length, which means the distance between the two lenses is equal to the sum of their focal length. What happens? It happens that after the two lenses, my beam is collimated again, and it is expanded 9 millimeters. Right? Let's see. I try to stay still. It's 9 millimeters. Yes. Okay. So it's 4.5 more or less, a little bit less maybe. Okay. So there is nothing much really special in what I've shown to you now. But I want to mention the fact that here at the focal plane, in between the two lenses, at the focal plane from this lens, we have a Fourier plane. The focal plane is a Fourier plane. If I wanted to do some spatial filtering, I would do it here. Can I do something here? Yes, I could. For example, let's see if it is still well aligned. Elvis aligned it. Let's see if it is still. Can you? Well, maybe you can see it from here. But if you come a little bit closer and you look, there is the central spot and all the others as well. Okay. So this is a DRE beam, the one that we've been talking about, and I would like to select, for example, if I want to select only the central spot, I can put here another pinhole that will reject all the other frequencies, all the ones that are around, all those rings, for example. After this, I have something that is quite nice. I think some of you might have already seen it because I the other day. Anyway, so this is a cylindrical lens. It's a lens that has, it's basically like a cylinder that was cut. It's not a, you can already imagine if it has a curvature that is only in one direction, it will focus only in one direction. So if this focuses only in one direction, we can blade of light. I can show you. My beam of so, but to align the system, we have shown the pinholes. When you want to align a system, what you want to do is basically make sure that your laser is passing through pinholes or irises, actually, and to use two mirrors, or you need to have 2 degrees of freedom. In this case, we align the system and this mounting that can tilt the beam, basically. Okay, I'm going to remove the objective because I want you to see a little bit better. Okay, so the idea is now we don't care. The lens that needs focus in a line. Okay, we saw here a spot for the cylindrical lens. The focal plane we should see a line. Now the focal plane of this lens is actually on the right now. Maybe if I put it here, okay, at its focal length, which is in this case 50 millimeters, I should see a line. Okay, so here we have a line. Is that if I move this piece of paper very quickly, you should be able to see a vertical line or a vertical light sheet. Can you see that? Okay, you can see that, but I'll show you what happens if I rotate it now. So if I rotate it, I will have an horizontal line. If I'm managing to, sorry, I will just move this. And if I move it from the side, you should see that it is like a standard beam, and from the top, we should see a plane. There is another way of visualizing this. So here in this cuvette, I have just put some highlighter. I just put put the tip of this highlighter in the water, and you can see so 532 green. So you green because the laser is, but you should also see yellow, okay, or orange. So I put something that is fluorescent in the orange. In fact, it is this one. So, okay, if we want to see better what happens there, we could use filter. Okay, so the filter is something that basically the wavelength that we are not interested in, for example, the laser. I don't care about the laser. I want to see the fluorescence. So I want to reject the green light, and I want to be able to see only the yellow or orange light. So this filter is a dielectric filter. So it doesn't work in absorption, but works in reflection. Okay? So it will reflect, in this case, everything that is below 550 nanometers, while it will let all the other wavelengths pass through. Okay, so I will use this in my detection line to get rid of the laser. But the nice thing is that if I look, I can see the fluorescence here. Can you try to? So first of all, don't take. If you look at the outside, okay, if you look at, okay, you can see what color. Okay, so can you tilt it now? Can I hold it for you? You look through? Now, if I touch it like this, do you see still the same color? No. Okay, so that's something. The electric mirrors or the electric filters, they work reflection and they are angle specific. They work incidence. If you arrive at a different wavelength. So now you hold it again and you go there. Tell me if you see any green. But color, you see the fluorescence. Yes, perfect. So if anybody else wants to it's just a green. It's nothing that special, but I want you to realize that with that filter we're going to cut the green, correct?
Morning again, we want
So
to
you don't
begin.
see green. Do you see?
Next session. Kindly let's
So
settle down.
If you look through, you should see that this solution, okay, great, perfect. So that you see the orange.
Want us settle down for so we are going to have the third presentation from Malik, to take maybe just to give introduction. I know a number of us have heard about nanotechnology. Now we have what we call the grandfather of nanotechnology. Malik is currently the nanotechnology, and in addition, he is a key board member Africa Laser Center. Also is a fellow of the and most of us are familiar with the Africa Academy of Science. A fellow in chemistry, the best headquartered in London. Fellow of the New York Academy of Sciences. Have been beneficiaries of that academy. Sciences, Fellow of the Islamic Academy of Sciences, Fellow of the American Association for Advancement of Science, Fellow of European Academy of Sciences. The list goes on. I don't want to maybe take the next 30 minutes to list all that. So as I welcome Malik also, together accompanied with him are the postgraduate students pursuing PhDs and masters in that field. So interact. So may I allow Malik to give us the next presentation, which will be on Maxwell's concepts to novel generation of coolants. We are talking about also nanofluids and heat and energy saving, which is a very key and presentation. Welcome, Malik.
Thank you. Program Director, junior colleagues, first of all, allow me again to express my deepest gratitude and to for allowing the possibility to share with you some of the knowledge that we have generated in the field of nanosciences and nanotechnology, and among those fellows who have generated such a kind of where is Nancy, Miss Nancy Mwenze and Mr. Juma Moses from Kenya, who joined us as PhD, and hopefully they will be in Italy for always under the ICTP somehow umbrella to expand their knowledge. And certainly next year they will be colleagues of mine, no students of mine, but colleagues of mine. Really the spirit. Late Abdul Salam, may his soul stays in peace. Today, it's titled From James Clerk Maxwell Concept to No Generation of Cool that apart important sector is the heat waste management and the heat waste recovery. Colleagues, all of us are aware about light and the description of light and its propagation. James Clerk Maxwell. You know very well the Maxwell equations. Done that, you have in a way or another, not in a very complex. He has derived them, but you the nabla and so on and so on. You have equations. What is not known about Clerk Maxwell, colleagues, extremely important, in effect critical and pivotal in LC, is that he has also derived and involved quite extensively in heat dissipation in materials, being gas or being into solid. And he has, we all are now, or we are, he has written a manuscript on Maxwell, the propagation of light, that he has written an extensive and a very sound book treating on heat management and heat propagation in solids and liquid and gases. And he was the one first who spoke, who has mentioned that there is a possibility to, or there is a need to come with a new type of materials to remove heat or to transfer heat. And I would like to share with you that, colleagues. During this section, I would please, if I will take, I will give an idea about, an overview about the heat waste, why it's necessary to recover this heat waste, and speak about nanofluids. What fluid. Then we go and the ablation is an outstandingly one single phase type of methodologies to synthesize this nanofluid. And we'll share with you some typical results which were, how can I say, our and in which number, in fact, maybe the message is my contribution is to guide the youngsters to embark in this, to get this result. And I will go with you, if you allow, for a start for these sections. What is sure is that colleagues, I am just advocate for it. It was done mainly by a number of fellows, but involving fellows who have quite a robust background in photonics and material science. That is Salah Hamlish from Morocco, as a previous PhD and then a postdoc. Karen Klute in, how can I say, she's quite good in life sciences and application, not only of the nanofluids in energy sector, but in medical. And of course, modeling, the computational, the Dr. Mahmoud Akbari from Iran, all of them nearly, and of course, Annelise Nangaosa, a PhD student from South Africa. So as you can see, different disciplines, different parts of the continent with different, how can I say, expertise. And the results that I will be sharing with you are, the experimental ones are the ones who have been generated by these fellows. And these fellows have published, I think, 2 or 3 papers in Nature Family Journal. Really, to how can I say, to witness these fellows from the South, or from the South, to come and produce knowledge of a high quality, but of a high value in terms of applications. So, colleagues, if the resolution is proper to any country, except the numbers are very high in the case of the USA, but the numbers are very low for other countries. Major energy as a China, of course, as you can guess, and Europe and others. But the most important message, colleagues, is that this section deals with the technologies which are used to generate, being hydroelectric, being it photovoltaic, solar in general, or being fossil. The most and energy correctly, but 50% of it is lost as a have used them. There is no other use them. Thermoconductors that we use are, but has the highest relatively to others. Other coolants has the highest thermoconductivity. Still, watt per meter per Kelvin. Simply said, that's the highest coolants. And because with the thermoconductivity, you have other parameters that you consider. So we have what percentage that we can recover. It is be sound indeed. So here, therefore, colleagues, just to get the scene clear for you, here is this negative one. The positive, how can I say, the positive landscape technologies that are used to generate heat, to generate energy. But technologies which are used to generate energy have a positive CO2 footprint, which means that if you use them, you will generate CO2. And that if you use them correctly, they will be they will maybe use them to, and we are obliged unity try to push as maximum as possible to use these technologies. As you can see, there are, for example, here you can see air conditioning, the usage of the VO2, the thermochromic smart windows. This is it here, as you can see. This is air conditioning. So it is necessary to use that technology that we presented yesterday together. The most important is the fuel efficiency and water and fuel also so we need to ones, and both of us to would understand is by nature. What can I say? And developing is a must, and I can assure you, if you have a laser, most advanced, how can I say, you can generate the most advanced nanofluids in a single phase, not a multi-phase where you have your nanoparticles, then you take them, you put them in a fluid. Okay, so here it is straightforward. To get a clear I'm giving you a colleague of a car that workplace using how can I say, radiator. Sorry, it goes to the engine, it removes the heat from the engine, and it goes back again hot. It goes to the radiator with a fan, it's cooled, and it goes back again. But at each cycle, colleagues, but at each cycle, colleagues, this is water. You remember, it has a low thermoconductivity, less than 1 watt per meter per Kelvin. High is the landscape of coolants. But you do understand, colleagues, is that the heat generated by the piston, therefore, water here with the cold water will remove only small, and therefore, at each cycle, it will remove just an amount of the stress. That means, second is that the engine will be using more fuel, okay, and more, so you will pay a lot from your pocket, and when it uses more fuel, it will generate more CO2 and more noxious, of course, gas. So you are obliged to think about coming with the new generation of fluids which would release the heat more efficiently. Therefore, you need to have a nanofluid which has a thermoconductivity above 1. Above 1, you are obliged. It's not a wish, it's a must. being it a hydrogen car-based car, being it fossil fuel, whatever, the engine is the same. You need to have a new coolant. And for such colleagues as light-based scientists, we have to come with a solution or to see the normal heat transfer which are used, mineral, ethylene glycol, and water. The ethylene glycol is the product which is either red or blue or pink. It depends on the country. We use it in the car as an antifreezer. And the organic materials also, as you can see, all this family of the coolants that we do use have a low thermoconductivity, less than 1 watt per meter per Kelvin, while metals, colleagues, and their oxides have a high thermoconductivity by 2 orders of magnitude at least. Therefore, the idea of James Clerk Maxwell is to use a mixture of these metals or their oxides embedded in a standard fluid coolant. That idea is really marvelous. You do understand that thermoconductivity is an additive thermodynamic component, which means that if you put particles of these metals in suspension in one of these, and specifically in water or ethylene glycol, you will have a higher thermoconductivity, at least somewhere there. And this is exactly the idea of James Clerk Maxwell, except, colleagues, except not able to make nanoparticles. They were large particles, then they're mixing with the water, taking whatever. And you do, colleagues, you do understand when you have a big particles, when you put them in a fluid with under gravitation, they will settle down. But if, and you will lose the notion of a nanofluid, but if that small enough, like nanoscaled, with a size less than 100 particles, will take over the gravitation, and therefore the nanosuspension will be stable, and therefore the notion of a nanofluid will stay. And that is exactly why only in the 70s, 80s that the Department of and when you remove that heat, you allow the engines. One and second is that you make that heat waste, you can recover it and you reuse it again. Colleagues, the idea is to use nanoparticles of this suspension in one of these fluids at least. Okay. It consists of nanoparticles in suspension in a standard coolant. This standard coolant can be this host fluid, you name it. And these nanoparticles here, these particles can be metal or an oxide in suspension. And you would understand they are so small, so the gravitation is not high, but will make it in a way that they will move and they will not settle down. The notion of suspension of nanoparticles in a host fluid is still valid. Then, the metal, the thermoconductivity, an additive component of a composite is somehow a thermoconductivity of the host fluid, and directly just of the nanoparticles of the metal or the oxide. And from historical point of view, colleagues, from 18 and different stuff, you can see there was a huge quantum leap in the 1867 to something in the 90s, where indeed DARPA wanted to revive this idea of nanofluids, because it is extremely important to remove heat from the nuclear reactors. That was the idea from the engines of, how can I say, avionic systems. It was the Department of and Eastman who came forward with the first papers and the first conference related to the nanofluid. And it's really hot. Not much people are involved in it with the. So it's a really, and jump on in particular with the what has the thermal lensing. I mean, new techniques which real, and here it is really the case. And colleagues, what happened is that the applications are not limited to, of course, removing the heat stress from in nuclear reactors, industrial cooling, solar energy, as you will see, both for the CSP and photovoltaics, and nuclear reactor as well, targeted, but geothermal. Kenya and Ethiopia have the largest, how can I say, geothermal capabilities due to the Rift Valley, and of course nanoelectronics to remove the heat from nanoelectronics. Use that heat and current data centers. There are two heat generated data centers is huge, and the idea is to remove, to waste, to recover it, and to inject it to the grid of the smart cities. That case, Google is currently implementing. It's one in Taiwan, one in one in Singapore, one in Norway, and the other one in Finland, whereby removing the heat from the data centers and convert it and inject it to the how can I say, to the grid of the city grid. And the most really non-explored is the usage of in the biomedical field. It's a really hot topic here, where the nanofluids can be really a part of bio solutions. And in that regard, we discuss possibly many of first in a classical approach was James Clerk Maxwell is stated that the thermoconductivity consists of the static one. Static one is due to the thermal host plus the of the nanoparticles. And the Brownian one is due to the motion, the Brownian motion of these nanoparticles. The static one is has been derived using an approach type of Clausius-Mossotti in electromagnetic. Derived this, whereby the Kc is the thermoconductivity of the, can I say, of the host material itself, and it's equal to 1 plus that term, and that term depends on the concentration of, as well on the thermoconductivity of both the host and the nanoparticles inside. And as you can see, colleagues, it tells us really, if you optimize this very well, if you choose metal in the form of nanoparticles, with the correct shape, and you will be able to have conductivity, the K static, just the K static, higher than the host fluid activity of the host. Therefore, you can have an enhancement of the thermoconductivity. That is, now in addition, motion will add on this K static. But at least here, colleagues, you clearly see that you put nanoparticles in this diameter and the right concentration, you will be able to have an enhancement of the thermoconductivity, and that is what I would like to share with you, colleagues. Of the ideal and the most simple, but the most beautiful, but extremely effective approach to make nanopulsed laser ablation in liquid solution. This technique consists simply of having a beaker whereby you have the target from the material that you would like to synthesize, or copper oxide, carbon, and you do the laser ablation in the host liquid coolant that you are targeting. Here, in a case, it can be water or ethylene glycol, mineral oil, and of course, you would choose a host fluid which has a higher thermoconductivity, such as water or ethylene glycol, and also you would choose a host fluid which has a good dipole, molecular dipole, to ensure that the nanoparticles, once they are formed, they stay in suspension and they will not coalesce. And how can I say, to have an homogeneous formation of the nanoparticles within the container, you would rotate the target and you will be ablating the different parts of the target. And colleagues, this is more or less the equivalent of a LIBS, except colleagues, here you are working at a regime where you are ablating material and how can I say, and you are not interested by the spectrum, but by the material which is ablated. And in effect, Juma and Nancy have synthesized this kind of nanoparticles of silver to do surface enhanced Raman spectroscopy, correct if I'm wrong. And the application of a system is to bioconjugate nanoparticles made by this laser ablation, not for nanofluid applications purpose, but rather to detect special molecules used in drugs or used doping materials, and the other one for Nancy, drug delivery. Yeah. So just to show you, colleagues, that in effect these nanofluids are not for nanofluids, but this technique can be used in particular in the biophotonics. What happened, colleagues? It's the mechanical complex, the laser ablation in liquid solution. It's quite complex in a way that you are ablating. You will have a hot zone of the target, and therefore you, how can I say, you are melting the material, so that you have atoms which are ejected from small clusters, and you have a cavitation, sound reverberating, laser matter interaction, and this shock wave pushes these small clusters, small atoms, to form clusters and to form nanoparticles, and these nanoparticles indeed are formed in an homogeneous way in the fluid, and you end up getting a fluid. And here, colleagues, what we have done is that we, instead to go nanoparticles of specific material in a fluid, we went a little bit, said, let's make a type whereby we have silver nanoparticle in white. Graphene is a sort of, you take a carbon and you peel atomic of this carbon. It's a Nobel Prize type system. And colleagues, so what we have done is graphene carpets, and let's decorate them with the particles of silver. Why we have chosen that? We have chosen these two materials because graphene is the material which has the compound that you can imagine better than diamond. In effect, it's a diamond type. It consists of layers. You are peeling layers of carbon and at room temperature, and this, it is the metal activity. That is why we have done this. We have combined these two systems, and we have made this composite in ethylene glycol and in water, but we are interested in ethylene glycol in particular because it's used. We're targeting potential engines of luxury cars and so on. And colleagues, here is the typical transmission electron microscopy of graphene carpet, as you can see. And you can clearly see with the Raman spectroscopy, clearly see the D and the G and the 2D and the 2G peaks. That means that you are in a presence in the graphene, not graphitic carbon, but graphene. And these are nanoparticles of silver, as you can see. They are not, here you have carpets, and here you have a nanoparticle type. And carpet, highly decorated with these nanoparticles, as you can see. These small dots here, they are nanoparticles of silver grafted on to the graphene. And of course, colleagues, you have to take into consideration the viscosity when you consider these particles in the ethylene glycol. So you have to go and more simple formulation of the Brownian motion related to Einstein equation, now for the Brownian motion. Colleagues, for thermoconductivity, we have to use a technique. It happened that the techniques that used are mainly laser-based. Unfortunately, we have none of these laser techniques, but the thermal lensing that it was proposed, shared to us by Humberto, is an ideal technique. I mean, in addition to, how can I say, the equipment or the facility seems easy to explore a possibility of mounting such a unit here in Kenya and another one in South Africa, and we should duplicate such a kind of sample units all over the African continent and the globe if need be. But we are ready from yesterday to embark in implementing such a kind of unit. In our case, colleagues, what we have used is we have used the hot wire method. We have used the hot wire method. We have made one homemade, but we acquired the new one, and the new one. I will not go through the details. It is the most technology, but the how can I say, the thermal lensing which was by Humberto is really far better, more accurate, or easily to be implemented. In the hot water, please, due to the limitation of time, I cannot go through the stuff. Please forgive me. If you need more details, we can give you the references related to it. What is sure, colleagues, here is the thermoconductivity within the range of 60 or 50, like this. It is the regime, the temperature regime, where the bulk of the engines operate. There is 200 degrees Celsius or no. Here, colleagues, and you can, the ethylene glycol, its thermoconductivity is around 0.7, like this. When you measure, when you use the thermoconductivity, when you produce the ethylene glycol with silver nanoparticles grafted on graphene, the thermoconductivity, colleagues, jumps from this value to around 0.40. What's this here? We are jumping from 0.32 to 0.40 is not much. Now, there is a jump of the thermoconductivity has been enhanced by a factor of 33%. It's massive. If you speak to thermoconductivity engineers or thermal science or technologies engineers, they will tell you that to move from here to that, it's massive. And it's massive because when you operate within the exchange of the heat and so on, the change. So as you can see, colleagues, if you take the nanoparticles on graphene, that side, if you take graphene, I call you, so enhance the thermoconductivity. But if you take silver decorated graphene, you increase by higher values. So whenever you use the nanofluid, it is higher than the host. Just simply said, it is higher. How can I say? It is a static one. Okay? This is the static one. This static is over Kc equal to 1 plus. So that 1 plus, the plus is related to this increase. As you can see, colleagues, the thermoconductivity of in nanofluids which have been measured so far worldwide are the highest, and the highest one that has been around, you can say 18%. We have that we have reached is 33%. For the moment, the nanofluids experts, all of them agree within the international nanofluid expert community. They agree that this one is the highest ever reached for the moment. And now, colleagues, how can we estimate the Brownian that we should not neglect? Well, the thermoconductivity of the effective medium number, we said it's equal to K static plus the K Brownian, as was mentioned by what is mainly focusing on this. But what is the which allows not only calculations and so on, you will find Brownian motion is proportional to the temperature somehow. And the Brownian motion, colleagues, the diameter of the nanoparticle. Of course, but to square root of the temperature. And when you do that, colleagues, on other type of nanofluid, in particular these silver nanoparticles, within that, you can see clearly, colleagues, that after a certain temperature, there is an increase. there is an increase with the temperature. Indeed, this Brownian motion component contributes to the thermoconductivity effectively. It's in the form of the square. And colleagues, what are the applications of these nanofluids? And this, I will focus on mainly solar energy, and solar energy, and maybe you the data centers aspect. While the hot topic that we should really embark, and that is where Moses and Nancy went in. And colleagues, for the photovoltaic, you are aware that the photovoltaics are cooled by what? By water. Why? Because, how can I say, the sun, any increase by 5 degrees, an increase of 5 degrees, as you can see here, colleagues, reduces the efficiency of the photovoltaic by at least by 1%, if not to 2. So, colleagues, we need to cool down photovoltaics, ensure that the efficiency is always around 13%. And therefore, we need to use the water. For the moment, the usage coolant is water. Imagine if you could, how can I say, colleagues, use a nanofluid, and that is Salah Khamlish, the fellow from Morocco, has created his spin, whereby the idea is to use nanofluids to cool down photovoltaics. Of course, it's not limited to photovoltaics, CSP, because for the CSP, colleagues, what you have is a system where you are concentrating light, and the light is absorbed by the selective solar absorber, converted to heat, and the heat is through the stainless steel tube or the tube to the liquid, here to the fluid, the oil, and the oil, as you have seen, conductivity or water conductivity is less than 1 watt per meter per Kelvin. Therefore, all the heat is not absorbed and transmitted. If you fluid in this system, you would catch all that heat is to be, how can I say, to be transformed accordingly. As I mentioned, in Singapore island of nanofluids is tested by Google to remove heat from data centers, and therefore, colleagues, there is a massive amount that have to be produced. It's a mass scale, and the idea, colleagues, in Singapore is that the heat is captured from the data centers and injected in the grid of the city. And that's more or less the concept of green cities. And again, colleagues, I wish to, for this, so to express my gratitude to the IC. And I wish to thank you also. I would just finish this section by stating, like, to state something of a wise man and wise woman in this regard. Yesterday, late Jomo Kenyatta, and today is Nelson Mandela, who says it always seems impossible until it's done. All is possible. Thank you.
Give the hands clap. Thank you so much, Malik. Just on the spot on. Going to hear the importance of nanofluid. More important, even in the Kenyan sector, the energy sector. The challenge of waste, energy waste, is a big challenge. And in Kenya, we have two different types. But there's another one in ports, the theft waste. So, but I think here we are more so on the system wastages. Allow me to ask the to give a comment or maybe any question to Malik before we continue.
Thank you so much for. I only have one question. But, when you are introducing these nanoparticles, maybe I have from a different element. I'm introducing them into the host fluid. Logic dictates that the amount I'm introducing will also, in another, affect the conductivity. I'm asking if there is a way we can quantify that. Just how much should I introduce? How much will that affect the conductivity of the result nanofluid? Thank you.
Thank you so much for that question. Indeed, it's extremely important. Generally speaking, what is observed experimentally, that 10% in volume is the limit, and from that increases. There are quite a number of factors on it, depending on the shape, depending on the size, but 10% volume is the limit. You are right, it's maximum is. And still the theories are not, how can I say, do not agree, do not guide towards that limit threshold of 10%, but 10% experimentally, yes. Thank you.
Yeah, thank you. What is the suitability of the base fluid?
Well, you are absolutely right. Also, it's another parameter is that because the ideal is to have nanoparticles dispersed in the fluid. You would favor nanoparticles with the zeta potential, which means if they are charged, the particles will not coalesce, and therefore they will be stable in the solution. That's one. And second is that if there is no charges on the surface, that means you are obliged to include the stabilizer, to use polymeric based stabilizers. They will conjugate on the surface of the particles and making it not coalescing. But generally speaking, for a small concentration less than 10% in volume, the stability of the nanofluids, in some cases, it can be around 3 to 6 months. But you are right. Indeed, it's a factor that has to be considered. You would understand that if you use an anticoagulant which would stick on the nanoparticles, you are creating an interface between the nanoparticles and the host fluid, and therefore that interface layer will block somehow, affect the heat transfer from the particle to the liquid, and therefore by, how can I say, successive stuff to the other particle. What we are looking for is around 6 months.
Thank you for your very nice presentation. I want to know your opinion. As we know, the thermal conductivity is related to the amount of the power that is transmitted. We have also the thermal diffusivity that is related to the speed of the electricity. and they are somehow related, but not always they are the same. In some applications, yes, the most important is the thermal conductivity, but there are in which also the thermal diffusivity is. Can you explain more about this?
I must admit, there is, for the moment, there is a conflictual discussion on this subject. What we, from the technology side point of view, they focus more on the thermal conductivity, the itself. But there is definitely conflictual matters between the thermal diffusivity and the thermal conductivity, the macroscopic one.
Yeah. Thank you. Any other question? Juma?
I think mine is important for those who are in the fluid for medical application of surface enhanced Raman spectroscopy. That is me, Nancy, even Mora here, and Caro. So the work was done, initial work was done in Chiromo, University of Nairobi. So the system for laser ablation and producing nanofluids, if it will be of interest to you, then you don't need to think about going so far. And I think our principal technologist, Mr. Mucheni, is down there. So we really appreciate the University of Nairobi for this work, for the initial steps of our project. So thank you so much.
Thanks.
Thank you, Juma. Malik, you topic fuel efficiency, which in the spectrum, of course, for those of us who are in the energy physics, a case study in sub-Saharan is the cement factories where they actually consume a lot of energy in our entire energy. And for those of us in energy audits, especially in these factories, we have found out that there are also heat losses or wastages, for the fluid inside. This can be due to maybe the poor insulation. It is for you, your focus is on the microscopic aspect, the generating the nano. With the technology now, we hear about maybe some of the FD tools that lab are maybe using, like maybe the ANSYS, and maybe you can give us the specific structural interaction tools that you maybe will be using. If there is a way, we can also share with maybe our researchers who are in this field. Thank you.
Really pointed to something extremely important. Instead, how can I say, instead of experimental testing and so on, it's a time-consuming, and the use of this type approaches is pivotal. And now that requested some of the fellows in the computational field that come in, and we will be started to interact with whoever has such a kind of capabilities to work with us. We have the high professional center in South Africa. Certainly you have also in Kenya, and we can use the CTP also to be able to identify some ideal materials where the nanofluids will be stable with the time and so on. And it's like a machine learning, how can I say, it will allow us to optimize time and to get straightforward either towards a system which of a value of an importance. So theoretical modeling is really paramount, and we are interested to embark in such a kind of study. Thank you.
Thank you so much, Malik, and for your information. We who are in the Kenyan academia, we are also learning from you. You kept on referring to us as colleagues, even to our students.
Correct.
Sometimes in the Kenyan or in our local institutions, there is a gap between the learners and the teachers. But I think, thank you.
Thanks a lot.
If you are okay, you can proceed.
The second one, colleagues, again, I wish to express my gratitude to the program director and to the organizers and to all of you, senior and junior colleagues, for giving us a stage to share with you some additional applications or laser techniques and but light-based tools in investigating the hidden functionalities and the properties of nanomaterials, materials at the nanoscale. You are aware that next year is the year of quantum, not quantum mechanics, but quantum sciences. Soon the United Nations will, how can I say, announce it. And the idea is to create what quantum sciences has allowed us, being in physics, being it in engineering, being it in life science, and so on and so on. How can I say, it is targeted that we will be having quantum computers, which will be faster than ever, a lot of heat, and so on. So I will single out two typical examples, but I will start with something. One of my colleagues, I think, Germany, had singled out Anderson localization. Correct? I say that. There was a fellow from Germany, I think, who has spoken about Anderson localization. And this is a beautiful phenomenon. Because Anderson localization reflects order in disorder. Statistically driven, it's mechanic driven. To share with you that, and if I also single out I go to point out on this matter because it is a really a way. The second one reflect on the contribution, on a massive contribution of late Abdus Salam, who was a founder with Prof. Budik. Soul stay in peace forever. I will embark in the first one, colleagues, that is the localization and localization, and to how matter and light, how can I say, interact, give you, which is a really peculiar. It's impossible. If simply said, colleagues, if I use a pointer, you see a red, and if I put it like this, close here, you will see my finger is becoming reddish. Why? Because the laser inside my finger is scattered by the, how can I say this? How can I say? Anderson localization tells me that you can have a case whereby your laser pointer, your laser beam, which is scattered finger, at certain moment it will come out as a beam. So this is impossible, but it is. That is quantum mechanics. It is. Statistically, it's, how can I say, it's extremely low probability, but it is, and I would like to share with you that. And remember, colleagues, what I mentioned about the peculiarity of nanomaterials dependent, their property, the size dependent. Take a big particles of gold, they are orange, and they like gold. If you take them small enough, less than 100 nanometer in the diameter, they can be green, they can be yellow, they can be red, they can be blue. Why? Because the electrons which are confined in that nanoparticles of a gold have a limited space in, and they are confined, and that confinement gives them quantum mechanic behavior. That means they will behave like a wave packet. They don't behave like as now that a transport of electrons, but they will have as a wave packet. Also, colleagues, if you remember yesterday, the gold that I shared with you, it also, the color of the gold nanoparticles, it's not size dependent, but shape dependent. And the nanoparticle form of spherical nanoparticles like this, or like in the nanofluids, or the graphene silver in the nanofluid that we have seen, or like carbon tubes, rods like this, or multi-layer coatings as you have seen, or as all the mirrors that we use in optics, generally speaking, as either multi-layers or sandwiches. Today, colleagues, ones. And in the real world, the carbon the nanoparticles, you find them like this polystyrene type nanoparticles. These are squared platinum triangular particles of silver and nanobars of gold. So these carbon nanotubes, and you see that the behavior of light in this carbon peculiar. As I mentioned to you, you send the laser beam from the bottom here, you will think that it will be scattered many times, governed by green function, whatever. It will be scattered many times that this light will come from this side or this side very weak, but it does not come out straightforward. No, quantum mechanics tells us yes. And I will, the second case where I would like to share, if time allows, to share with you how we can trap neutrons in Fabry-Perot resonators. When you do Fabry-Perot in optics, you know it very well. But when you take it at the nanoscale, you can trap neutrons, and you how can I say, you can neutrons, and you can link this trapping of neutrons to the standard model of Abdus-Salam, Weinberg model, and of course you relate this stuff to the Big Bang theory, creation of the world or the universe. Well, anyway, I will start, if you allow me to show. Anderson is a really, you may say, it's a pure model. It's a mathematical model, and you are right to accept that it has an outstanding impact in modern sciences. You know that why the sky is blue. We know why the sky is blue, because scattering is 1 over lambda power 4. And therefore, the infrared, the large wavelength, and therefore the scattering of the infrared is quasi-null, quasi-zero. But when you go to the shorter wavelengths coming from the sun. They are heavily scattered, and therefore the have heavily scattered gives this blue color of the sky and reflected on the sea. It looks like us as blue. So all of us, we knew that there are quite a number of regions. There is the me scattering, there is the, how can I say, the scattering, but there is, these are the classical ones, and of them, they are related more or less of the particle that is scattering this light and the wavelength on which the light is interacting with. So, in the case of me and the Rayleigh scattering, the lambda over d, where lambda is the wavelength of the light, and the d is the average size of the particle diffusing or scattering the light of wavelength lambda. The ratio will either give you or Rayleigh scattering, but there is another one that is called Anderson scattering, localization scattering. This Anderson localization is a purely quantum mechanic behavior. It was proposed in 1956, and what it tells us, this Anderson localization, I will not go through the details. Colleagues, please forgive me. You can go and dig on the literature to have a clearer view about the work here. But the work that I'm presenting, colleagues, on Anderson localization is the work of an MSc student. We have observed the phenomenon, but it took us a huge amount of time and the weekends and so on. So we said, you know, let's give this to a student who wants to have a cum laude. Succeeded to get this, to observe this phenomena. We have to write robust support for her to get cum laude. So what is Anderson localization? There are three regimes: weak, strong, Anderson localization, an average, a medium Anderson localization, and a strong Anderson localization. In this case, we are sending a light with wavelength lambda on semi-disordered material. This disordered material have scattering particles which are semi-disordered. It's not a huge disorder. There is a localized order, but in general, the particles are disordered. And when you scatter light, it will be scattered just slowly, and it comes out. But it comes out in different directions. You have the average one, whereby your light with times also intensity. Other one, strong localization, is where the regime where your light is carried any time. It comes out in the beam here, the initial beam. And here, colleagues, just simply said, if the scattering by it will be scattered by many of them, and it will come back in each scattering center. If it comes scattering center, isn't it? And that is, if you have this configuration, you may say this is impossible, but well, quantum law on different systems. It was observed by Chow in the disordered powder. If you take a disordered material, and the light which would come out, it will come with a single wavelength, with a high intensity, and therefore a disordered material will laze. Why? Need to have a laser, very good mirrors, and so on and so on. We have observed a lasing effect in the disordered materials. This is impossible. The point is that it was observed experimentally, and other materials have whatever. Colleagues, we have, how can I say, on carbon nanotubes, because the carbon nanotubes are ideal. They are very long, very, can I say, very long and highly ordered if you synthesize them correctly by pulsed laser ablation, for example. You can have very long, highly ordered, highly crystalline carbon nanotubes, single wall. In addition, carbon nanotubes, depending on their twisting, they can be semiconductors, they can be metallic, or they can be insulators. So we took these carbon nanotubes for this reason. If they are metallic, that means they will reflect and the infrared region in any source, generally speaking, polychromatic, is very high. For the sun, infrared is about 52%, while in visible around 43. I think it's around 5%. So the usage of carbon nanotubes, the carbon nanotubes, you have them. You can have them. You can have them those spaghetti type. You can have the spaghetti. Them this, isn't it? So they are long, yes. These carbon nanotubes, they are long. They are disordered. They don't have different shapes. It is not this one that we are looking for. It is this one. And here are carbon nanotubes. I'm going to say very long type. And remove this graphitic stuff. You have only, I'm going to say, long and highly crystalline carbon nanotubes that you have by laser ablation. And what we do, colleagues, I do not want to go through the details. The idea is to say, in that powder of the carbon nanotubes, we could have the situation where we have a light beam reflect to be, how can I say, and it will be reflected by the carbon nanotubes. It will be scattered by the carbon nanotubes and directly be reflected by the carbon nanotubes. In particular, if it is infrared radiation, and if these carbon nanotubes are single wall or the multi carbon nanotube, but very carbon nanotube, if they are twisted and they are metallic, therefore they will be infrared reflecting. And if this beam is reflected by these carbon nanotubes, it will definitely, statistically, will be reflected, other carbon nanotubes close to it. Because imagine you have many needles close to each other. And you may think that this one will be reflected by another carbon nanotube somewhere here, and once reflected by this one, it goes to another one, and it comes back to this one, and therefore you will be able to have an Anderson localization, and that is the case, indeed, colleagues. And colleagues, what we do, we use attenuated total reflection approach. Why? Because the ATR is a purely infrared, and because when you put your carbon nanotubes here under the crystal or on the top of the crystal, you may think that I will be sending the beam here. It will be reflected times. and each time it will be interacting with the, how can I say, with the carbon nanotubes here. And therefore, the reflections will definitely allow me to see as being within this carbon. Well, and you use the ITR because it's, how can I say, an evanescent wave, and therefore the electric field is heavily concentrated in this direction, in this plane, and in this direction, and therefore you have a high probability to excite to such a, how can I say, localization of light, if any. And colleagues, that is what we obtained when you do many times. It's statistical, of course. Here is in the spaghetti type carbon nanotubes. You observe such a kind of. Here is the absorbance versus the. And colleagues, you may say that, oh, there are some interference, some fringes. They are not highly contrasted. So it's a really, you are in a doubt here to say, okay, fine, there are some interferences, but they are not clear. But when you take the sheep-shaped ones, this is what you get. It's a fantastic interferogram. That means there was really an interference type. How can I say? You say, how can I explain this? Better than that, when here is you go from to but you go above 3,000 to 500, you can clear these fringes. How can I say? Some interference type resonances somehow. To explain why we have this, and one way is to say, in the sheep-shaped carbon nanotubes that I have used, either light, the sheep-shaped carbon nanotubes resonate, can act as entered here, it goes to this, propagates to this and here, and it will be reflected, coming back, and so on. So therefore, you are considering the carbon nanotube as a resonator in lasers. Well, when you do such a supposition here, you will find out that to consider that this, how can I say, this possibility is one. The other possibility is that the light through here, and it went, and it has been reflected by the second phase, the first phase, second phase, third phase, and so on, which it has done like this. Which means the light, the infrared light that you send has been localized somehow in this direction here, in the basal direction, not in the longitudinal. And the third example, you say, this interference can be due to an Anderson localization type. So and single out what is this, what is like this, what's the probability to have that, and what's the probability to have that. And colleagues, when you do this, colleagues, due to the fact which has within which the carbon nanotubes, each carbon laser have it, since the infrared went reflected by the end side, coming back to the first side, the second side, and so on many times. Well, colleagues, when you measure the contrast, you will find out the reflectivity of the end must be above 66%. This is impossible for carbon nanotubes, which are just simple number of layers of light. Let me just go back for you. Oops, sorry. Yeah, colleagues, you see here, this is the end section of the carbon. It's just some layers of carbon here, of this carbon. Just layers, not a huge amount. So this carbon cannot reflect light at 60%. It's no possible at all. Therefore, that's a position of us that, how can I say, this interference is due to this configuration is not possible. If you agree with me, if you tell me please why, and we will definitely go to renew the experiment. But how can I say, that is the case. What's the second case? The second case, we said that this interference might be due to the interference, not the longitudinal one, but transversal one in the carbon nanotubes, doing this, tuck, 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 and coming back. And this is what we call again, is the ancestor of the Fabry-Perot. And here, when you measure the fringes, the distance between the fringes, you will find that in this interference, these fringes are in a micron. Carbon nanotube can't be therefore. So therefore, the Lumaguerre for the unique that our light has been confined in an Anderson phenomena, and therefore the cavity which gave a birth to that interference is indeed Anderson localization. And colleagues, in addition to that is that you would see, colleagues, if you remember, you would see here that the absorbance, which is the log of the absorbance decays in an exponential, and the exponential is another fingerprint of the Anderson localization. And therefore, colleagues, in this case here, that interference that we obtained indeed is due to a strong resonating Anderson localization, and not Fabry-Perot, not a Lumaguerre resonating configuration. And that would bring me, colleagues, to the end of this section here. If it allows program director, I would like to share with them. Otherwise, I can do it but I would like, just please, before you leave, I would like to appreciate through another example, if I am allowed by the program director, how the impact of Abdus Salam. You may think Abdus Salam is the standard model, it's quark and so on. No, this has nothing to do with the lasers and light. No, you are wrong. The program director, he gives me the green light.
Please go ahead.
Thank you so much. As I mentioned, for this, we have requested, yet my name was the first I do not deserve, but she has insisted and she has acted accordingly. I do not deserve it. Late Longo was an MSc student, and because we have a colleague, Ndumizo Tingo, the phenomena, was really very, how can I say, accommodating and collecting a huge amount of spectra. You remember this statistical phenomena, so you can get it once, it can come back, and you, well, anyway, she was the one who took of her time to get us that beautiful spectra, and she got Audi indeed, and she got a number of prizes in effect related to this research. The one that I would like to share with you is is related to cold neutrons trapping in Fabry-Perot resonators. Again, colleagues really work of how the late Abdus Salam. And because I was awarded the Spirit of Abdus Salam award with these famous colleagues, and in fact I do not deserve it. I am not at the level of these two deserving fellows, but nonetheless, the example that I would like to share with you is related to the theory of these eminent fellows and Abdus Salam and Stephen Weinberg. You're going to say the theory of these fellows is to come with a single model whereby gravitation, electromagnetism, and strong and weak nuclear that is. And how can I say? And this theory of Abdus Salam is more or less to the lifetime of a neutron. A neutron which is bound to a nucleus can live a long time, but a free neutron, its lifetime is limited to 15 minutes, not more, approximately 15 minutes. And that time life of the standard model and a model which has been proposed by scientists. Why is that? Because it will decay. You say, damn, what the hell is this? He's speaking about something which has nothing with the light, with the lasers. No. Free neutron will die, will give birth to a proton, electron, neutrino. If you have a proton and an electron which are close, what they form? What is the element which consists of an electron and one proton, please? Hydrogen. Thank you so much. When two protons are close, helium, correct? Therefore, a death of a neutron gives birth to all of Abdus Salam, because the universe due to that. And therefore, how can I say, we came with an approach to more or less the lifetime, or to have high precision the lifetime. And you do a neutron is a particle. Fine. And that the neutron, in effect, is not a particle by se. It consists of two down quarks, one up quark. You may think, oh, Malik is an expert in the field of high energy. No, my background in that field is at the 0 degree Kelvin. And let me just precise it. But these cold neutrons, their energy is so low, it's so low that they behave like a wave. And that is why it becomes good, it becomes interesting, because these low ultra cold neutrons do behave like a wave packet, and their behavior is like X-rays. Whatever you see with X-rays, you can see it with these neutrons. I will not go through the details, colleagues. I have had the honor and the chance to be supervised by the unique PhD students of that is Professor Motrauch in Vienna, and he was the one who introduced me to this field here. I will not, please forgive me, copy is with the organizers. You can have it. The point, colleagues, is that we use the total reflection. You know this experiment, isn't it? All of us, we have done this experiment of total reflection, where we send a laser beam at the interface of water and air, and boom, we have a total reflection. And we know that the total reflection here, the angle of total reflection, is related to the refractive index here. We know it. We can do the same thing for Browse, for the polarization, and so on and so on. That we do use, but this total reflection can be observed with the neutrons, and if it's used with the neutrons, we can see absolutely fantastic phenomena. And if you have the neutron beam, you send it neutrons. If you have normally the neutron beam and the total through propagating for such time inside this material, and by being transmitted within the second reflector. So this is a Fabry-Perot nanoresonator. Neutrons, another one, but separate power of reflection of neutron wave packet. What you see, colleagues, is this. You see reflection here. This is the total. This is the reflectivity of Fabry-Perot resonator, colleagues. This is what you see, and here that is the beam we're measuring, and the beam in transmission. That's what you see in the black, colleagues. And what happens, colleagues, here is that these dips in the total reflection plateau are due to evanescent waves which have escaped, resonating here out. So for each dip in the total reflection plateau is a maximum. That tells you that the neutron wave packet, first of all, the neutrons, it tells you that, first of all, you have a reflection and transmission. That means the neutrons that you are handling behave that they are not particles by say, but have total reflection, as was observed by Fermi, is that the neutrons are checking the wave, the Broglie lambda equal to mv. If you remember, and that you are checking exactly what Fermi has observed. Remember, he has observed this total reflection before engaging in the first, in making the first atomic bomb. But the first total reflection that he has observed, which was pivotal for the atomic bomb, is that he has observed that in Brookhaven National Laboratory. Now, better than that, colleagues, and that brings me to the hot, is the maximum of this in the total reflection. That you will be able to now to get the how much time this neutron wave packet which have tunneled, how long time have been trapped with the resonator. If you do that, colleagues, this is you have the time that they have spent in this resonator, and for how long time you have trapped them. And colleagues, you see, this is in long, short period, precision in the picosecond. But there are two techniques currently, colleagues, which are what we call a bottle and the beam method. The precision of trapping is plus minus 2 seconds, and this one is plus minus 0.6 seconds. And here, colleagues, this here is plus the type. So you can see using a Fabry-Perot resonator, you can reach very high precision. I had paper had been invited. I told them, no, colleagues, you are. I said to the professor Suits van Bag, I told him, I think you are mistaken. I am not. He said to me, are you in South Africa? Yes, when we were together. He said to me, are you in South Africa? I said, yes. Are you the nano man? I said, nano man, I don't know, but I work in the sciences. So he said, are you the one who has done his PhD in Newton optics? I said, yes. I said, it's you. I said, maybe it's another man. Yeah, well, Uppsala, so I can jump. And they asked me to present a point. We discussed it. I said, no. Well, let me repeat myself. I am Malik Maza. What is you are speaking about? He showed me the paper. I said to him, this is indeed, I co-authored this. Basic or borrowing from traditional optics and combining it to nuclear sciences, it brings us to something which is a really hot topic. The precision that we are capable to Newton and far higher than the traditional ones, the beam and so on. And that, how can I say, colleagues, the that govern more or less is one of the elements of what we call Kobayashi-Mascow matrix. I say this is the first parameter which is the standard model. As again, my know-how in that high energy physics is at the 0 degree. And I thank you for your thanks.
Let's give Malik another hand clap. Thank you so much, Prof. And maybe for purposes, any question? I know you have informative insights about the nano field, but maybe comments from our participants. Any question?
Presentation. My question is regarding the first part of the presentation on Anderson localization. We know of two-dimensional perovskite occurring quantum structures. Can this observation be made also in these 2D and Popper materials, which are quantum well structured?
In fact, it would be definitely ideal for us. In Holland, working on molybdenum sulfides, observe Anderson localization in 2D systems. Yes, the group of London.
Thank you. Any question? Any other questions?
So I know you mentioned in your presentation that your level high energy physics like 0. But looking at it where there is interest along high energy lines, are you seeing people going to search for neutrinos and what? And of course from your presentation, there is a moving forward to maybe high energy physics, in your work.
I'm not certain. My expertise in the field of high energy physics. The beauty of it's multidisciplinary. And you have speaking about traditional plants. And I felt that it's disciplinary. There's so much to be discovered at the interface between disciplines. And in the high energy physics, I have to admit, nanophotonics, major breakthrough. I think if there's a breakthrough, it would be photonics, where light and material science and material in general will link. There, for example, in the memory loss, a new type of memories a new type of chips will definitely involve light and how can I say materials at the nanoscale. But I do feel that, how can I say, wherever the wave takes me, if there is a good science at the interface, I am back. And it happened that this is the ideal aspect of university. That is why I was just mentioning to my colleagues here is that maybe it's time, in view of what I have noticed and what I have witnessed during these 2 days where I am here, the high quality of the photonics is carried out by colleagues here in the National Institute of Optics. I think maybe it's to think about having a UNESCO chair in photonics, and we'll be delighted to support such a kind of initiative. I do believe that the support of the Trieste system and Italy in general would be a really sound for such UNESCO chair in photonics here in Kenya specifically. Thank you. I hope that I responded to your question. Thank you.
Thank you. Thank you. Anyone? But in case we have more questions, I think Prof is still here. We can maybe meet him during lunch hour. Let's now give him a hand clap for the good presentation. Prof, thank you for your informative presentation. Now we go to the next presenter, who I would like to give an introduction just before we go for lunch. And I want to thank all the participants for your attention. That simply means that the topics and presentations actually are of interest to you. You know, with all these speakers who are coming from different experience fields, we are able to also nurture our young researchers, and even those who are still in the lab or who are doing research for some time, we are able to update ourselves on whether whatever we align with what the scientific community can consume. Malik, thank you so much. We have your contacts to actually extend the partnership. Who have actually Kenyans. So it means they have a home where you can mentor our laser students. Thank you. And I've given you right go ahead. You can start with even some partnership or work with us. to introduce a colleague who is also an expert, a household name, Karatina University of Kenya. He earned, again, not the optics, and he has an extensive research experience in the field. Also, in physics from KU, and a Bachelor of Science Education with a major in physics from the same university in 2007. He happens to be our visiting scholar also at the National Institute for Optics and Lasers. He teaches for us a number of units for our MSc students. And also, lately, I also introduced him to many our undergraduate students. We have a Bachelor of Science in Applied Optics and Lasers, where he's also taking a unit just to make sure that our students get the best. So I want to introduce Stephen, my good friend, to actually come and give us a presentation that second pulses. So let's join hands and we invite Stephen on the stage.
So thank you very much, Dr. for that introduction. As it has been said, my name is Dr. Njebe. I'm based at Karatina University. And today we are asked to discuss about isolated attosecond passes. That's the topic that I look at today. So that's where I work. Okay, it's a green for those who maybe have some time. They may visit the university. Okay. So this is how I'll make a presentation. I shall start with a little bit of introduction. I shall discuss about the high order harmonic generation. I shall look at the high order harmonic generation in gases and also in solids, mostly about the solid orientation, and also discuss a little bit about the ongoing research in this area. So this issue of isolated attosecond passes, no, high order harmonic generation, I think discussed, we had an introduction, Professor who came a talk, and mostly what she based her topic on is mostly on high order harmonic generation. But in my case, I'll go further and I shall discuss isolated attosecond passes. So just to give a brief review, like in our previous discussion, this was mentioned about the Nobel Prize, and this Nobel Prize of 2023, whereby the people who got this Nobel Prize, they got Nobel Prize as a result of the generation of isolated attosecond passes. And I would like to ask, we have a recap of how this comes about, and the generation of isolated attosecond passes came into birth as a result of what you are referring to as HHG, or high order harmonic generation. So in short, when atoms or matter is illuminated with light, high energy or intense light, phenomena that are expected, we have one is a threshold, the double ionization, and we have the HAG. But the former two, that's a double ionization and above threshold, they don't really do much, especially when it comes to the generation of isolated atomic compasses. So in this case, we have a diagram on the right here, whereby we have a femtosecond laser pass, and this femtosecond laser pass is projected to a media, and this media can be either a gas, mostly we have them be generated from the gas, and what happens that we end up with the X-rays, what you are talking about, the attosecond passes. And one thing that you must know that for this to occur, we must be deal with a laser intensity of about more than 10 to the power 14 watts per. For us to understand the issue of the high order harmonic generation, we should a little bit do with the harmonic spectrum, and this is very one is generating attosecond passes. And the formation of the harmonic spectrum of generation of high order harmonic was only established or was only realized with the invention of the lasers. And the first spectrum was obtained in the year 1987. This was done by University of Illinois, and in their work they were able to use the laser pump. This is a krypton fluoride pump laser, and the media that they were able to use was neon, and using this they were able to obtain harmonic orders up to 17th. And these harmonic orders up to 17th, these are very short, okay, harmonic orders. And when I talk about this much interested with is this +2 region, okay? This is what when you're talking about harmonic orders of up to 17th order, we are only considering the plateau region, because when you talk about the harmonic spectrum, it comprises of 3 sections. We have what we refer to as the perturbative region, and in the perturbative region, you find that the intensity does increase, and the region of the spectrum occurs when there is no emission, okay, of the pass, but this region is the most important part. The current research that is going on is to ensure that we have a longer plateau region, and in case that we have a longer plateau region, what happens that we shall be able to get shorter and shorter at isolated. Second group that tried to generate harmonic spectrum, this was in the year 1988, and in this case, they used the neodymium-ion laser, and their target media was argon. If in most of these experiments that were done, especially when there was the use of the gases, those are preliminary experiments. The media that they used were the noble gases and elements used the noble. So the third group also who tried to also to come up with was in 1900, okay, and in their group you find that they were able to obtain harmonic orders of about 109th, okay, and as you can see, as each group proceeded, you find that the harmonic order was increased, which is to the advantage of the generation of isolated attosecond passes. The last group that I can discuss, not the last, because even now it is being carried out. I'm only talking about people who are pioneers. We have the 1, 2, and again, person also was conjoined in the winning of the Nobel Prize, and in this case, they were able to produce orders of about 38 harmonics. So for us to understand this is obtained, there is a theory. Professor Fetar also talked about it, and this is a 3-step model, which is also commonly referred to as a simple model. And in the simple model, what it discusses about is that talking about the generation of high order harmonics being as a result of illumination of matter with light, and as a result of that, electrons are dislodged, or they are removed from the surface, or they are energized, And when they're energized, they're able to obtain higher energies. And as we know, those back to the so using that the outcome, okay, then okay, according to the theory, and we find that as we say that there is the illumination of the media, and this media, as I said, it can be a gas or it can be solid. And when this happens, we have an electron is, and this electron is excited and allowed to accelerate or to move in presence of the high intensity field. Okay? After that, it has to come back to the parent, or it rejoins the parent. And when it rejoins the parent, there is an emission of a photon. Okay? It is well described by this expression that the electron combined with the parent release a photon whose energy is given by ionization potential 3.17 UP, which is a photomotive energy. And if this photomotive energy is dependent of or the light source that is used, and also the wavelength. So these are very important parameters when one would like to generate passes. But one thing that one must also put into consideration is the process that's a 3-step model. It just takes place in each and every half a cycle. So that at every half cycle, an emission of a photon. And as a result, end up with what you find train of, okay? And when you're talking about a train of passes, the train of passes when it comes to the applications. So in that case, we have some schemes, and the purpose of these schemes is to ensure that instead of us getting a train of passes, we can only be able to get an isolated one that you're talking about, the isolated attosecond passes. Okay. This is just an explanation of what we are talking about, the ionization and all that. And when you're talking about the ionization recombination process, there are two paths that these electrons, or when they take. We have two trajectories. One trajectory, and we have the short trajectory. And how are these achieved? The trajectory. These are electrons, okay, that ionize just about 3/4 of the optical path, and we get ionized beyond the one optical cycle. So one of the in short, we see that the long trajectories occurs. These electrons, they ionize. It takes a longer time, and then it takes also a longer time for them to recombine. Short trajectories, these are electrons paths that take place in that they take a very short time for them to be ionized, and also they recombine within a very short period of time. About the issue of the train of passes as a result of the presence of two trajectories. So any time that you want to come up with the isolated attosecond passes, what you do is that we have to eliminate one of the paths so that you are present during the process of formation of the passes, and when one of them has been eliminated. So when they are talking about the modeling, carry on modeling simulation, have equations to guide us on how these passes are generated. And as I said, the first thing that you have to do is that you must find high harmonics, the 1 dimension, the 2 dimension, 3 dimension, but for my case, I've just considered the 1 dimension here. So, and also what you are referring to as the potential to the interaction of the laser interaction. But the atomic potential, you find that it's dependent with the soft core. Okay. When you are talking about the potential due to laser, which is given by VR, E, in this case, this electric field can be, you find that for those who have read about, or they have interacted much about the formation of atomic pulses, isolated you find that this field can be enhanced, and we have that are used of who came up with application. The one who came up with that was able to win a Nobel Prize. But in my work, I used what I refer to as a plasmon, and this technique in the year 2000. And maybe in my discussion still, I shall to discuss much about it. Can be expressed using this expression. Okay. That is of more importance, the generation of the spectrum, or that's the harmonic spectrum. The generation of the harmonic spectrum of the dependent dipole acceleration, which is expressed by this expression. And finally, you can be able to get isolated atoms. And when you have the superposition, what you do is that we consider the plateau region in which you find that the intensity is constant and the harmonic orders. Okay? And when you superimpose harmonic orders, when you find that you may either train or isolated attosecond passes. Question again was asked during Professor Fatal's presentation. Should you generate isolated attosecond passes? So for us to be able to interact, or for us to be able to know the electronic atoms, and when a man is able to move the subatoms, we have conquered the world, because we cannot be able to get the basic of matter, which is atoms. So in my work, in my discussion, I want to discuss part of what I did in my PhD. So the first part I'll just discuss is about the generation of isolated attosecond passes when it comes to the first case I shall look at the gases, and the second case solids. Okay, so I shall discuss part of the generation of isolated attosecond passes in a multi, and also we shall look at the control of polarization direction of isolated attosecond. The reason why we have to look at the polarization direction, if we can be able to change the orientation of isolated attosecond passes polarization, it means that what we have done is that we shall have improved the areas of applications. But most of the activities that we have, or they are not on a linear. Results. As diagram here just represent the electric field. This electric field is 800 nanometer wavelength with optical cycles of 30. So this is how the electric field of that laser is. So from this, I can also be able to give the get a good understanding of the harmonic spectrum, we carry out what we refer to as the analysis. Okay? Frequency analysis, we have two peaks. Okay? We have the longer ones and we have the action of short and the one that are reading. And these modulation structures, talk about them, they are not beneficial, especially when one would like to obtain what we refer to as isolated passes. The reason why, as I mentioned earlier, to be able to obtain isolated passes, what we do is that we do the superimposition of several superimposition of orders about 90, because if you look at it, it is not smooth. Okay? As a result of that superimposition, what we end up are these are passes. And this case, we refer to them as train of passes because we have passes which are emitted at different optical time. But this one can be eliminated by schemes. One have polarization gating as some of the schemes that are used to obtain isolated attosecond passes. So the second part of my presentation here is when feed is this is when a two-color field is used, and in this we have the 800 nanometers, which was the previous one. This was in the one-color field. We have the introduction of the 2000 nanometers. So in this case, the 800 nanometers is the driving field, and the purpose of this, the 800 nanometers, is to excite the electrons, and the motion of the electrons within its path before it recombines with the parent is controlled. So as a result of that, we can be able now to see the change in the harmonic spectrum, and the structures have been decayed. And what again has happened is that the harmonic have improved or it has increased, which is also very beneficial to the formation of isolated attosecond passes. So when again, as I mentioned, to understand this, we carried out what we refer to as the time frequency analysis. And after carrying out time frequency analysis, these are the peaks that you obtain. They are key to get isolated attosecond pass. We look at the section with which we have as the peak. And in this case, we did the superimposition from about 250 to 400 harmonic orders. And as a result of superimposition of harmonic orders from 200 to 50 and to 400, having attosecond pass, okay, and whose time duration is about 40 attoseconds. And you find that this seed is a bit high because when you look at the electrons within an atom, it oscillates at a lower. We have that point. The other thing, again, have the issue changing of the polarization in the case where we have the two-color field. Okay. In case the angle of polarization or the angle at which is oriented to the sample is changed, and for our case, this second case we have the frequency analysis of that in our previous. You find that the formation of isolated attosecond passes of about I did that 7. It's not very clear. So another thing that when you're talking about of this, because previously what you have done, now we have introduced plasmonic enhancement, which I think I have a slide that I shall discuss much about it. And you find the effect of the variation of the inhomogeneous parameter. In this case, when we are talking about the inhomogeneity parameter 0.01, okay, and as a homogeneity parameter, the cutoff point is increased, we shall be able to, okay, or we shall be able to eliminate either of is our angle beams. That's the angle in which the two beams are oriented to the amount of photon. We see that it be what you refer to as the intensity control pass from the you still have there is that or the plateau region. That the same case that happens as a result of increase in the intensity. But as careful, because when this the intensity with the result of that what you refer as isolated attosecond pass. Now I want a little bit when you talk about the homogeneity parameter, what exactly, how is it achieved? And from our physics, how charges get concentrated or how charges are concentrated in material. In this case, we are having triangular shift and know that the charges are more concentrated at the peaks of them. Now, which are V-shaped, you find that the charges will be at the tip. So in that case, in case now we have the media being placed at that point, and then we a source, you find that because of this field being high due to the point electric fields which are there, you find that there is the and of electric field means that we shall get more intensity, and therefore we are able to unlike in the previous case, we see that the minimum of intensity must be 14. In this case, we are able to use the intensity to power 13 because of the enhancement of electric field due to the use of the plasmonic enhanced tips. So the expression that is used to show for us to be able to determine or to calculate the electric field due to the plasmonic enhancement by this expression. Another thing we look at is a polarization control, and in this case we are considering the association by we consider the two-dimensional. Okay, we look at along the x-axis and that's our field, whereby one of the is along the x-axis and the other is along the y-axis. And in this case, we want now to see how one can be the polarization of isolated attosecond passes. In our calculation, we also we look at the ellipticity, and you find that at the perturbative part of the spectrum, there is that too much variation of the ellipticity. You find that one cannot either you are dealing with either linearly, circularly, or elliptically polarized. Okay. As such, again, we carry out the time analysis and still we discuss the x-axis and also along the y-axis, and we are able again to determine the isolated attosecond pass within the two dimensions. Again, at the middle there, we have the resultant. The along the y-axis and also along the x-axis, we have a pass at one section. That what we have here, we are able to only to obtain a train, and then we can be able to see the angle at which these passes are generated. So we further look at the two-color field, and in this case, we are able to do proper isolation of isolated at second pass within the x-axis, and as a result of that, we are able to get peaks when you look at the time frequency analysis. And again, we look at the spectrum along the, find that there is that, in this case, when there is that superposition of harmonic spectrum within isolated attosecond passes, which is about, I think 64 attosecond passes, and the angle is also well determined. Again, you find that by the virtue of us introducing the second color, one can be able to see the ellipticity is varying, and you can see that it's also resembling, almost resembling what that we obtained. Around 250 there, up to around 400, the ellipticity is 0. Harmonic orders, within this region, what will end up are linearly polarized, isolated attosecond passes. And actually, in our calculation, we are only able to obtain linearly polarized isolated attosecond passes. Otherwise, in a case this that we have mounted here was maybe at a certain point, maybe at the middle here, means that we shall be able to obtain value of 1, meaning we have obtained circularly polarized beam. But we failed the investigation homogeneity parameter variation. That you vary the inhomogeneity parameter along the x-axis. We see the effect of this, and by varying the homogeneity parameter, in this case, when we place along the y-axis to be constant, what you can see is that as that value change, what you can be able to see is that there is that efficiency. One of the limitations, and I think in this, of the limitation of the attosecond pass efficiency. It's used to attosecond passes. And how do we know that there is that conversion efficiency that is decreasing? We look at the cutoff region, and the cutoff region will guide us vis-a-vis the intensity that is at the cutoff region. You find that sometimes this point moving down and down. As a result of it moving down, it means that what we have, that harmonic efficiency is decreased. Okay, so to obtain by the y-axis was being varied, and in this case you find that the harmonic efficiency was really low. For each of them, to their So the other study that you have done is the HAG in solids. You find that the production of isolated compasses has really taken another dimension, and have too much now being done in terms of the solids, how we can be able to obtain the isolated attosecond passes. The reason being is the solids HAG spectrum has high harmonic efficiency. And as a result of that, it means that it will be able to overcome, okay, are with the in. Just to understand that, what we do is that we look at the model of a solid, And what we are much interested in is a value conduction band. Okay? But the moment this material or semiconductor material is illuminated with the light of intense, you may find that energy from the value conduction band. And that it moved the first conduction band, the second conduction band, or the third conduction band. Okay? And able to move from conduction band. In this case, it is only a little amount of energy to move it to that point. Remember, an electron cannot be held. So when this first conduction and some other electrons move to either the second or the third conduction band, when they come back to the parent, they come back to the valency band. What is that they do is that they emit a photon. And depending on the position that electron was after it has been ionized, you find that spectrum. For gaseous spectrum, you find that they have one plateau region. But when it comes to the solid spectrum, they have more than one plateau region. And simply this is dependent on the position of the electron after it has been excited. At which position has this electron to? If it has gone to the conduction band, when it comes back, we shall have the first plateau. If it goes to the second conduction band, when it comes back, we have the second. That. But in this case, you find that the second plateau that is formed is efficiency. Okay? So there are schemes that are used to ensure that we can efficiency of this. So this behavior is well described by the which I think I in my. So these are the papers that again we have discussed much about the formation of isolated atmospheric compasses in solid, and mostly we have looked at the nanowire, okay? And we have looked at the nanowire in a homogeneous field and in an inhomogeneous field. And in this case, we are looking at the orientation of the nanowire. When the parent or the laser is you can see that there is variation of the first harmonic order. So as the angle increases, you find that the first one is 0. We find that the plateau is at a higher region. When the angle increases, that still keep on going down to a level whereby when the angle is at 90, the harmonic spectrum, that is the first one, is at the lowest state. And we have done the time frequency analysis within the angle between 0 to 180, and you can be able to see how the spectrum is, and you say that continue decreasing up to 90, whereby it has the minimum intensity, and from there again it starts increasing. For us to be able to solve this or to be able to obtain this, we are guided by the 10 Hamiltonian equation, which is in the lecture. Okay, I think again I will not discuss about this. We are also having or guided by the Matthews type potential. Okay, in this case, we consider the being a very certain value. So some parameters I have not presented. Okay, again we look at the effect of variation parameter. See, as a homogeneity parameter increases again, there is that increase in the harmonic spectra, as one can be able to see from this. And then for this case, talk about and when you look at the first plateau is at a higher yield in comparison to the second plateau, but for the second plateau, you find that the introduction of parameter increases the harmonic yield of this, which is also, as I said, quite beneficial. The passes. again to how this is coming about. In this case, we didn't use the 3-step model for solids, but we use what we refer to as time-dependent population inversion imaging. And in this case, what we do is that we calculate the number of electrons within a certain. Okay, so for the first case, this one we are the issue of the homogeneous field, and one can see that the bands, and in terms of the number of electrons, it's well distributed, but you find that the moment you introduce a homogeneous field, the intensity increases, and again, electrons which are to the first. Okay, so this is a schematic diagram to show how electrons are able to move. Current. Maybe something that is worth mentioning is that we're talking about the conduction band. How it resembles when you look at the, or we discuss about the Bloch theorem, and you can see an electron valency band will be able to jump to the conduction band when it is at this position. This position, that's where it requires minimum energy for it to move. So within, again, there is that oscillation before it comes back to the valency band. So we have again to look at the electron population, and in this case, this is well illustrated using electron population graph, and maybe it's not quite visible after it has been illuminated, but you can see that when this is the case that you are talking about angles, and you can see that when you are talking about the angle at 90, you can see the population is so low. But again, as this increases, you find that the population increases, and this I think is about at 30 degrees, that's orientation. So we see the total electron field. This is a conduction band 1, and you see that due to introduction of homogeneous field, as we mentioned in my presentation, that the electrons are more energized, and we shall have more electrons being. Okay. The same happens at different angles, as we have discussed the harmonic spectrum trend. The second conduction band, you find again the angle increases. So homogeneous parameters, and case peaks others, but the time-dependent population image has electrons second conduction band. But again, one has to be very careful even when you're talking about the aspect of inhomogeneity parameters. So we look at the polarization dependent case. We are the angle of the nanowire. And nanowire, a presentation I've only given for the conduction band. Population decreases to 90, and then it increases, as we are able to see from the spectrum. Similarly, absence of the parameter. For the case of inhomogeneity parameter, a different trend was observed. That in the first case, you have, as the increase from 0 to 30, you have that increase in terms of the population, and then at 30 degrees is the maximum population that is attained in the second plateau, and then after that, there is the decrease to about an angle of about 75. Then at 90, there is a slight increase and then decrease, and then like that. And this happens in both cases when I talk about the the homogeneous and also the inhomogeneous field. So these are some of the ongoing research. Okay? And one of them is the generation of isolated attosecond passes when you are talking about the two-color field and the static electric field. And the purpose of this is to see whether one can be able to increase the energy. Okay? Though it has been all investigated the effect of inhomogeneous field, by the addition of static electric field, we would like to see what exactly happens. There is also an ongoing research on the high-order harmonic generation in doped semiconductors. And the purpose of this is to see the effect of doping in generation of this. Another research that is undergoing is polarization of the phase holograms. Okay, in this case, we want to move from the linearly polarized holograms, and because of also their limitation in terms of the applications. So we want to see whether by coming up with changing the polarization orientation and coming up with polarized phase holograms, whether we shall be able to make a head-on in terms of the improvement of the diffraction efficiency. There is also research on the spectral noise reduction in holograms. One of the limitations, again, in the application of holograms is the spectral noise. And we want to look at a scheme that can be able to reduce the spectral noise to achieve our objective. Gate. And again, we want to see whether we can be able to improve further, ensuring that we get less and less attosecond passes. So thank you very much, and welcome. So, any
questions? Okay, thank you so much, Dr. Ali, for that. It was highly informative. Now, the first question, you have seen that the population increases with the angle. And then you have seen that the spectrum, it goes decreasing as we go towards the 90. Can you people maybe to explain why is it that the population is increasing and yes, the spectrum for the one we had shown before is that increasing?
I have not gotten your question. Well, can you?
Yeah, you are saying as the angle increases from 0 to 90, as the angle increases from 0 to 90, is an increase of the populations. But there is a graph you have shown somewhere for the one for the gases. The spectrum was low. So I wanted to know why is it that when the population is decreasing and there's the second question is that does this passes be determined the energy of the laser by the intensity of the laser or by the laser? Because for you to have the Planck region, the one we understand, is it determined by the energy of the laser or what determined by it? That's all. Thank you.
Start with the last question. You talk about whether it is determined the energy of in some of the presentation, that the intensity of the beam plays a critical role, and the wavelength also plays a critical role. Okay. Again, when we are generating this, we are choosing the intensity and also choosing the wavelength. One must be very careful so that you find that most of the wavelength that I use are about 800 nanometers. We have to look at a wavelength that can be attainable, and we can come up with lasers which are operating at that wavelength. Okay? So that is one thing. But also I mentioned that one also must be very careful, and that's why you find that there are different schemes, like the plasmonic enhancement, the chipped amplification, and the purpose of it is to ensure that we don't have too much intensity which cannot be achieved, and we only use low intensity which is amplified. And to get that. So the other question is about population. Okay. So these are two streams. We are talking about the solids, talking about the gases. Okay. I mentioned when it comes to efficiency is low. Okay. And because of the low harmonic efficiency, what we do is that we jump now to the use of solids, because solids have promising in terms of the improvement of the harmonic efficiency. So when it comes to the gases, mostly we don't populations. Okay, the population is only looked at when you're talking about the solids. The issue of orientation. Remember, we have two different type of materials. We can have isotropic materials and anisotropic. Okay, and these materials, some of them, the properties of it is based, and some are isotropic directional based. Okay, so in this case, for the nano wire, it is directional based. Depending on the orientation, the properties of this material will keep on changing, and for that reason, that's why we see different population in terms of electrons. Thank you.
Another question?
For this comprehensive, really enlightening contribution indeed. Thank you so much. I have noticed that how can I say, attosecond are polarization sensitive.
Yeah.
Correct.
Yeah.
I think chiral molecules would be ideal system to be investigated with attosecond spectroscopy if we need. That's the first. And the second, from Njoroge, just to follow up on one of the first slides that you have showed us, that in effect attoseconds became as the way to investigate the dynamic of electrons in the hydrogen atom by what's her name?
Neon.
Another lady from Sweden, the Nobel Prize, Anne L'Huillier.
Yeah.
Anne L'Huillier, with stroboscopy, dynamic of the electron in the hydrogen atom. Just to that it is highlighted and literature is attoseconds would allow one day to allow on that aspect, please.
So thank you very much. I think as when it comes to the attosecond, mostly what has been done, but very few labs now, mostly that has been done is theoretical aspects, and actually in our work we are doing it theoretically, and I think with the I can't remember the and they want is physical things. Okay, I can't remember the place, but I think as you have mentioned, the moment this breakthrough is obtained, I think we can be able to have diverse application of this, even if when it talks about the investigation of the colors. Okay? Because it is said that, right? I hope men in the room can be able to say this, but maybe one application can be, it can be able to distinguish different colors. When you talk about blue, at which blue color are we talking about? At which blue? Yes.
Another question?
I just like some clarity. When you talk about these higher order harmonics, which are being produced by the solid material, how are they being detected? Because I think that the semiconductor material will absorb